Okay. So, meta model of meta mathematics. Well, actually, it's really mathematics. Okay. So,
Okay.
pool of patterns. I'm going to use your examples here. Okay. And then, all right, that's a pool of patterns. Now, what you want to do
Those are basically tokens, gonna be our tokens. And they are patterns because we don't care about like any semantic meanings of those. The only thing that we care about whether the names of patterns that we give them are the same, where any event acts on them.
You mean, well, okay, let's look at that in a specific example, okay? So what is this? Is this real?
Yes, this is like, you can read it as E as an element, right? So the first pattern is basically 0 is an element of natural numbers.
Okay, let's call it LM or something, okay? Just for the sake of us. I mean, I know it's cheating because it gives us some meaning to the thing. Okay.
Right. Well, that's why they were labeled that way. It was just to make sure that we weren't clinging to anything, semantic.
All right. Okay. Well, fine. Just let's not use. That's fine. I'm happy to use E, but let's not use capital E because it does actually mean something.
Yes.
Okay, and then we're going to change that to lowercase n. Oops, what's that? Let's call that NN. All right, let's understand what these are. So,
well, now you have like mixed up. So,
what have I mixed up?
oh no, yeah, it's okay. No, you have like plus. Oh no, it's fine. It's fine. Sorry.
This thing here needs to be decoded. But I mean this, okay, so explain this to me. So is this an assertion? This is a predicate, basically.
Yeah.
But that predicate, you're saying in this pool, the Z blank here, the two Z blanks are the same thing. Is that correct?
By themselves doesn't matter. But if we have an event that takes both of those tokens simultaneously, then it should treat them as the same. But it can be not even be a symbol. It can be like an arbitrary expression tree. That Z. That could.
Oh, I understand that. I understand that. But I mean, this is the way it's going to work is. Okay, there is a pool of objects containing variables that can correspond to any expression tree. Right? So let's write down. So is this in fact, let me just understand what this is. So this is, I don't know what P is it. Okay, so let's write down what these things.
For plus. Basically
okay,
plus.
all right, okay. So let's write down what this is. So E blank, Z blank, N blank is basically N is an element of Z. Is that right?
Z is an element of N. Z is 0, N is natural numbers.
Oh, I see. Z, i.e. 0, is an element of the natural numbers. I'm surprised you end up naming the natural numbers here, but let's take a look at this. All right, so what's the next one here?
that's a successor. Basically, if A is a natural number, then successor of A is also natural.
So the arrow here is representing implication somehow.
Yeah, we do it there explicitly, but because like the first example that you have from the pool of patterns, you have rule also as a pattern. So this arrow also can be just an arbitrary head, basically, that you don't care about, right?
Yeah, I think so. So let's write it out that way. So then this becomes, let's say it's just
in
R.
practice, it's going to be more complicated.
Well, okay, fair enough. But I mean, if A, okay, so the next one, if A is a natural number, then so is successor of A. Okay.
Yep.
All right. If N is a natural number, then what the hell is this actually saying? There's just a plus. There's just a random expression hanging out there, isn't it?
Yeah, just a constructor for plus. One of them. And like, that's the next one expression is another one. And together they form definition of plus. A is like a conjunction, and it's like, yeah.
Okay. Is that enough to define plus?
I think so, yeah. For natural numbers. Perfectly fine.
All right. Well, if that's the case, okay, where's one? We don't need a one. We just say Z is a natural number. Yeah, so that's enough. Okay, so you're saying this thing here is enough for natural number arithmetic. So what are its rules?
They're also going to be like a specification of events. So this is like just pool of patterns is just our tokens, right? It's like space.
Yes.
But then you will also have to specify how our inference actually works.
Right. Right. Okay. So okay, now this entailment rules is basically what we're talking about. AKA events. Okay, so now what do we suggest that the events are?
Well, one obvious is the modus ponens, and you also had to add some logic in order to like have the conjunction work. So we had two rules there, which are very messy, by the way.
These rules?
Yeah.
Yeah, those accepts bother me a lot.
It's just, yes, it's just so that we don't apply rules to rules, at least, in order to at least make it less complicated.
Okay, but so let's just understand where this is going. So in this model, is this the case of arithmetic?
Yeah, almost. Yeah. I think it's still unclear. Like this.
By the way, is
no
token
great way
event
to
graph
form
is
conjunction.
I'm sorry, is token event graph now in the function repository?
I don't think it's still there yet.
So James, that's something we really need to chase.
Okay.
Okay.
I understand. Yeah.
I do have like publisher ID. I can publish from the Wolfram if I just publish it. maybe it just ignores the review.
I mean, if it's got some documentation, I would say go ahead and do that. And we can go and fix it later, okay?
I was actually thinking, like, why can't we make some kind of place when we just can publish without any reviewing at all? That is not visible to outside world. But
Yeah,
it's also
I don't see any reason why we shouldn't be able to do that. I really don't see any reason to not do that.
Because there's some kind of resistance always.
Well, I don't know.
Present some kind of resistance.
Who presents
The whole
resistance?
process. The whole review process.
Yeah, I understand. Is there a good reason why we cannot allow internal WFRs?
Because buckets right now work exactly like.
I know, to publish
Like that.
to a hidden well, I'm going to just evaluate this for now. Okay, so that was the token event graph there. Okay. So let's understand. Let me copy this into my thing here. Okay, so let me understand what this all is. Okay, where are you using the logic?
To construct list of rules.
So wait a minute. Okay, so those are the rules. So now, what is dilute duplicate patterns?
Just to strip away some vertices. All the patterns that match themselves basically in pairs.
And what do those patterns? Okay, so let's just do 2 steps here. And let's say well here. Let's just do for now. Oh, for goodness sake. Great. Okay. So let me understand what this is. All right, so let's look. So what we could say is, okay, so after one step, let's understand what this is. So after one step, Z is a natural number. Turns into the disembodied statement plus of 0 and 0.
Yeah.
As well as the statement n is a natural number implies.
It kind of turns into itself. So this event takes two tokens. One is the 0 is natural number, and another one like if n is natural number, then plus 0, and produces itself.
Yes.
And just does the symbolic plus 0 and 0.
Okay, well, so let's look over here. So in this event, A is a natural number.
I guess it should also produce 0 again. I think it
Implies, wait a minute, this is 0 as a natural number, and this is A is a natural number, and S of A implies S of A as a natural number. And so this is now saying the successor of 0 is a natural number down here, right?
Right.
So that's a proposition. What's interesting about this is some propositions are ones that we would assign a truth value to, and some are just disembodied random thingoids.
Yeah, then we have to have tokens that represent equalities and the truthiness, true and false. And we don't assign the semantics beforehand. It's just a floating.
No, I understand that, but the very fact that the process, the pool of patterns, can contain patterns that do not assert a truth value.
Well, yeah. Yep. But that's the goal. That's what we
Okay,
wanted to do.
Can the pool of patterns contain patterns that do not assert a truth value? Presumably, yes. I mean, presumably the truth value,
yes, of course,
is in the eye of the beholder, so to speak.
This is supposed to be a pool of arbitrary, not yet semantically, analyzed syntactic statements. So yes.
Yeah.
And then the question is, how do we get from this pool of statements to the kind of mathematics that we perform or observe? That's the
Well, I understand that, but can we get, with this, okay, we've got these entailment rules, which are a little bit complicated here. But the question is, can we actually can we generate, I don't know exactly why you're doing arithmetic rather than Boolean algebra, but maybe it's a good idea.
It just happened.
Okay.
I don't know why.
It happened to come up because we were first trying to obtain addition and multiplication just using a binary operator, and ultimately we had an identity for addition, for multiplication, and Nick started basically just generating naturals in order to create those identities. And I think that's how we ended up getting into arithmetic over natural numbers.
You mean over Boolean algebra? I mean, Boolean algebra. Okay, let's review this again. Okay. So what we imagine is there's a pool of patterns.
Yes.
You can try to make Boolean patterns.
Yeah, well, let's do that. But I mean, but the claim is we've got this pool of patterns, and these represent kind of the seeds of mathematics, right?
Well, the bag of seeds is much more capacious than this. But this was just an example of working with the pool, but with some sort of reference that we could understand. In this case, natural number arithmetic.
No, I understand. The full pool contains all possible pattern expressions.
And it's difficult to start working with those in the beginning because they're quite
I understand.
Alien and unwieldy. Yeah.
Right. But now, so the interpretation here is that we look at a certain slice of this pool, and that gives us recognizable mathematics. And one way to look at this pool I mean, in the Boolean algebra case, or just the arbitrary axiom case, okay, so simple case, single arbitrary axiom. Okay, so in this case, we've got this thing here. And if I'm not mistaken, we simply turn those into pattern variables, right? So, I mean, let me just write this out. It's this thing slash dot.
I think there's like a resource function that unformalizes symbols.
Oh, that would be useful.
Or it's the other way around. Yeah, unformalized symbols. There is such a function.
Okay, and then the equals sign. What happens to the equals sign?
It's just the same as the other binary operators here.
So you're saying we should change the equals sign to just be an,
Yeah,
Yeah.
pattern blank.
Okay. Okay, so now what you're claiming is that if I apply your laws of inference to this, that I will derive statements of Boolean algebra.
Well, not those laws are not enough. I think there's some.
What else
There
is
should
needed?
be more rules.
What
I
else
think
is
something
needed?
about equality, I guess, and
Okay, so maybe some rules about maybe transitivity and symmetry of equality.
yeah, reflection. Yeah.
Okay.
What else?
Oh, well, let's just do it. I mean, because we can have another axiomatic theory here. I just want to take a general axiomatic theory.
Sure.
And see how we are deriving its statement, so to speak.
Right.
And fundamentally, what we're going to be doing is I mean, what exactly is this modus ponens doing?
So it looks at two tokens. One of them should be rule, right? And another one, anything but rule. But it could be also a rule. So in general, right? But for example, so it finds those tokens and tries, and the output is just the application of this rule on the expression.
Okay, but there's a big special
If they
case,
match.
right? Because how do you identify rule from this pool of patterns?
You don't identify it in general because everything can act as a rule.
Okay, so what does this modus ponens thing do? Does it pick out every expression and just treat its sort of leading symbol as
it treats it as a rule? Yeah, if it basically identifies every binary and treat it as a rule. But it is just one rule from the rule yet. Don't care. Just if you include also all the rules, then it becomes even more complicated. So this is just one useful rule from the whole set of rules that potentially generates all the mathematics from the pool of patterns.
Okay, so you're saying I mean, one thing that bothers me here is that these entailment rules, we've got two different enumerations of all possible things. We've got all possible initial conditions.
Yes.
No, that doesn't count because like initial conditions could be generated from emptiness by just additional rules.
Okay, all possible initial conditions, i.e., arbitrarily sized pool of patterns.
Okay. Yeah.
Or could be generated okay, and then we've got potentially an enumeration of all possible rules. But right now you've got a very specific rule here, right?
Yes. Yeah.
Maybe the idea, because when you allow you actually rules to apply to themselves, maybe there is like, you see, like our theory, I have a comment there that modus ponens also lives there as a token itself. You know,
Yes.
so all our rules are actually has their representation as tokens too. So maybe everything we should have just a simple rule that just starts generating whatever rules, whatever tokens we have, and then we can use these tokens as rules too. That's
okay. But how do we? What is the ultimate? How we use the tokens, right? You see what I'm saying? I mean, let's say this thing is itself a token, right? Even though it's a little bit messy to write out here. I don't quite why.
There is a minimal rule that like is like in this sense universal. And it's like,
well, what is that minimal rule?
Well, that's the question. That's a good question.
I think it will probably be related to the substitution rule that MetaMath uses.
There's no substitution in MetaMath, actually.
How does MetaMath work?
This was a source of tremendous difficulty this afternoon.
Well, you can always send mail to Norman McGill. You know, he will answer.
Duly noted.
We just messed with MetaMath and I reviewed how it works. It's a stack.
Sorry, I'm back. Yeah. All right. Let's look at. Okay. So again, you know, we're seeking the simplest meta model of mathematics, right?
That's right.
And the model. Okay. Meta models of mathematics. Okay. So one model, possible model, equational axiom systems. You know, that's a very simple model in which everything is just substitution of expressions, right?
Mm-hmm.
That's a pure substitution model.
And substitution here means is like we have patterns in our pool of patterns where there's a binary pattern with the right-hand side somehow representing the left-hand side of it with like a rule.
Well, yeah, I think so. I mean, where this is basically saying the distinguished operator is equal aka and the two-way rule, basically. In other words, you can take any, that's a case where find equational proof.
Hmm.
I mean, let's look at an example of find equational proof based on, let's look at an example here. Hold on 1 second. All right, this should provide us with an example of find equational proof that is completely trivial. Let's try this one. Let's try this one here. B dot A dot B equals A. B dot, oh God, did I lose it? Is it this one here? Well, how about B dot B dot A equals A? Okay, so that's our thing. Now let's see what theorem we try to prove. Wherever that is. Well, let's just do okay, let's just say groupings of, let's say PPQ, comma F arrow 2. Why are there more of those there? Well, okay, so now some results here. Let's try doing well, that's totally trivial. That's going to be true. Oh, I see. No, it's not true. Right, because that isn't the right way around. Okay, there's certain results here that will be true. Let's find one that's actually true. Okay. Oh, I don't know how to find that. P equals P dot P dot P. Really? Can't I even do that by hand? Oh, this one I could do by hand. Huh?
What is it? You have axioms on the left, right? Or the other way?
No, axioms on the right.
Uh-huh.
Ah, finally. Now notice that that's a for all there. Okay, but I claim this proof Well, okay, so now let's look at the proof graph for this. Okay, axiom 1 was this thing here. Hypothesis 1 was this thing here. And then in one shot, they hit a conclusion. Does that make sense, everybody?
Yeah.
Yeah.
And the way they hit the conclusion is position 1, orientation -1. Okay, how does this proof actually work?
I think the proof function is going to be more helpful. So there's a map at the place.
Okay. Okay, let's come back around to this, okay? So what we're saying is, the question is, what structure do we need to have to make it a mathematics rather than simply like a universal algebra with a bunch of operations on binary operators? Making sense?
Yeah.
Let's see. Well, okay. Sorry, I'm just looking at one thing here. Sorry, I just need to make myself a note of something. All right. Okay, listen, we got to make progress here. Okay. The question is, again, you understand the model of mathematics that is based on, that I talk about in the NKS book, where we're basically looking at, these are tree substitutions, right? That's all that's going on here. To prove these theorems is a pure tree substitution adventure, correct?
Yeah.
It seems so, right, Nick?
Yeah, I mean, that's all that the equational
Yeah.
proof does, is it does tree substitutions. And the main issue is, where does it do the substitution, right? In every step, if we take an example of, I think I managed to break some things here. Hold on one second. Let's see.
think position doesn't matter. We shouldn't allow like replacement at arbitrary positions.
What do you mean? It has to.
Well, I mean, it's not a requirement to like to have an ability to replace at whatever position, position that we have.
Really? I mean, that's certainly how these things work.
Yeah, I know. I think it's like somehow related to this constructivist view. If you only restrict to the constructivist logic, you have to only replace at the root, because you can't replace at any subtree, because you have to, in order to do it, you have to construct it first. But if you want to do it, then you somehow already constructed this tree, so you have another access to this subtree in order to do the substitution anyway.
Okay, so if we look, you know, your typical, I don't know why we can't do this. Where is it? Okay, so there's some complicated set of axioms. But okay, so here, I don't know how critical pair lemmas work in this for these purposes. Do you know? Well, I mean, the idea of a critical pair lemma, it's using critical pair lemma to derive a critical pair lemma requires using the properties of equality. Okay, but what's happening here basically is we're making a transformation like that, right? At this position in the original expression. Am I making sense? So let's try taking in this particular case.
Yeah.
Is it like a substitution but with an argument? Can you say that?
No, I don't think so. Let's try it. Let's try taking the. Okay. So at position 2. Okay, so here. So we're saying replace part, replace map at, replace hash, comma, at position 2. What the heck? That didn't do anything there.
Well, your left-hand side of your rule doesn't match anything.
I know. Well, why does this think it does something?
Well, it's an output expression. That's what should be at the output, not the input.
Oh, okay. The input. Wait a minute. The input is this one here.
It's the same as output.
How could it be the same as output?
Maybe what it does, that's what it means here. Maybe input is, I don't know, written somewhere else.
Okay, that was critical pair lemma 2, I think. Was that hit this one here or no? Which one was it? This one here.
Yeah. Isn't it just the first one? Yeah.
Rule, matching rule, sub-pattern.
Well, hold on a second. This has a rule here. Okay. That rule, okay, I explain this. Can't
really explain it. I don't get it either. Yeah.
Well,
Could
this is what we
compare
have
it,
to
right?
understand. This is what we have to understand. What we're trying to do is we're trying to say, in this derivation, we've got these derivations, and they're basically obtained, I think, by substituting, pattern transformations into other pattern transformations. But I think it's weird. The role of the actual transformation symbol is weird. I need to get something to eat. I'll be right back.
Okay.
By the way, have you guys looked at, I think this confusion is exactly where I was, kind of this time last year. A little bit earlier than this, last year.
Okay.
Right?
About critical parallelisms.
What?
The confusion about critical lemmas.
No. The general question. I mean, so what I remember is there's case one, which is the expression goes to expression using an axiom. Okay? You have expression goes to expression, and that gives you a new, or essentially you're saying LHS plus, I mean, I'm saying expa, LHS goes to RHS, and that goes to something that's of the form expa goes to expa prime. Expa 1 goes to expa 2, which itself can then be used as another transformation rule.
Sure,
right?
sure.
Now, in the equational logic case, we have this same thing, but instead of a one-way rule, we have a two-way rule. Okay. And then our entailment rule is this very modus ponens like, except it isn't quite modus ponens, right? Because this is saying, and that may be the constructivism versus not thing, that LHS can be a subpart of the expa 1. Right?
All right.
Okay. So this is one model. Maybe this is the only model. I don't know. I mean, is there a different model? So I'm kind of stunned. Okay, what is model? Is there another model? Or is this the whole story? And then this model, this requires some additional rules for this, I guess. Because it requires telling you can flip that around. Well, I don't know if it does. Maybe those rules can just be rules of the same form as this. Does this make sense?
Well, maybe they should be decomposable into a pair
What's that?
of two left. Maybe there should be a rule to decompose it into a pair of left arrow and right arrow.
Yes.
At least.
But I mean, Yeah. Well, but I mean, e.g., the fundamental rule is with this thing, but there is a rule that allows flip around, reflection, reversion, reversal. Okay, but now an important point about these rules, these transformations, is that unlike, I see what you're saying. I mean, and reversal could involve rewriting what is a pattern variable. See what I'm saying? Because we could have something, whoops, we could have something where we say, basically, no, something like f of
two-way rule is always a pair of just usual rules.
Sure, but we could have this. The inversion of that is p blank arrow FPP. And that is just the blanks move around.
Yeah, and you can't write it as a two-way rule without any ambiguity. What is the variable and what's not, right?
Well, you're saying it's something like this. I'm not sure that that's without ambiguity, because I think there's semantics in the replacement.
It is, yeah. I think it's more complicated than that.
I'm sorry, which is more complicated? What?
I mean, it's not just replacing the variables with patterns.
What's not just replacing variables with patterns?
To make a summation of a two-way rule out of pairs of rules. If you have a pair of left-hand side, right-hand side, right-hand side to left-hand side, you can just make this a two-way rule notation that is disambiguous about what are you replacing, what would be the pair again. So we can decompose it always with just patterns. Maybe you can, but I'm not. It's not obvious. I think there is more complicated. I think there is more complicated two-way rule patterns that just made. Well, there's more complicated pairs of patterns that you can't just write it so that they could be decomposed or back.
Okay, wait a minute. Is there a notion? Okay. Basic design issue. Is there a meaningful notion of a two-way pattern? Right? I mean, in other words, if we have a if there is, let's call those TWPs. If there is, then our, our pool of expressions, our pool of patterns can just be a bunch of two-way patterns. And then our entailment rule just becomes entailment is just by a TWP to a TWP to get a TWP. Is that right?
Yeah. You can just say it the same about equality.
So what that's doing, it will always take, that's always of the form 2 goes to 1, right? 2 TWPs goes to 1 TWP. See what I'm saying?
Yes, yes.
So like in theorem proving, we're gradually pruning down.
Yeah.
I'm very
Yeah.
confused by this because, well, maybe that's right. I mean,
It doesn't sound I mean, if we're beginning with all these arbitrary patterns, two-way patterns, I mean, hopefully
look.
it reduces to something.
Look,
It
what we
prunes
have
down
to
to
do,
something.
until we have TWP1, TWP2, a 2-to-1 transformation that dumps something back into the pool is still perfectly reasonable and valid.
Well, of course.
Right? So
Yeah.
that would go to this. Okay.
Okay. So it doesn't destroy anything.
What?
So it doesn't destroy anything.
No.
Nothing is destroyed. Yeah.
I mean, mathematics keeps adding facts to its knowledge base. And
Well, meta mathematics keeps adding patterns to its pool. We have to make some distinction between this and mathematics. I don't think we're at mathematics yet.
but look, these are going to be statements of Boolean algebra and things. No, my question is, how much do we have to prime the pump? Is it the case
Right.
that,
It's a good question.
it could be sufficient to just take, I mean, is it potentially sufficient to just take, this as a two-way rule, and that's just the whole banana. That's the whole thing. But in a sense, the only thing to generate the statements of Boolean algebra, we just take that two-way rule and start applying it to itself.
Yep.
Do you think that's true? I mean, and that's all we need. Now, one of the things that's tricky is you made the claim, which I'm not sure I agree with. Okay, here's the issue. How are variables shared across TWPs?
Yes.
I'm saying because here, the fact is there are actually two things going on here, because the
Right.
center dot, should be shared. The individual A's, etc., should not. I mean,
Yeah, across TWPs.
yeah.
Yeah.
Why do they should be shared? With what? The only thing that it's known that they are the same. within one expression, with one.
I know, but the center dot should be the same across many TWP expressions.
Right. This is the idea of the operator basically being respected under transformation.
Yeah.
The operands being kind of ephemeral. The operands can it doesn't matter.
Okay, so what's the analog of that in hypergraph? The analog of that is
right.
What's that?
No, continue. I'm just
well, I mean,
nodding along, I suppose.
I don't quite understand it. I mean, the fact is, the rules in the hypergraph. See, the hypergraph has two things. It has a data structure in which atoms are shared.
Yes.
Because it has a rule in which atoms are shared as well.
It depends how you define like the equality between your atoms. So here we propose like equality by just structural equivalence. So it's like
Yes.
whether they have the same structure, not just like some kind of number. So you just name your center dot by just like some pattern name, and it just it shouldn't have like just a symbol. It may be an arbitrary expression too. So it could be a tree. It's by itself. That not just one atom, right?
I guess. Yeah.
So the only thing that matters is just we have the same tree somewhere else in some other 2WP that we can then apply our like entailment.
I know. Well, so you're saying, but the point is that generically, look, across all these two-way patterns, somewhere we expect pieces of those patterns to be essentially operators and constants. And there are some where we have just ephemeral variables. Okay, so I'm trying to understand the analog of that in the hypergraph case. Right? I mean, and we're claiming, okay, so in hypergraphs, the tokens are hyperedges. In our case, they're trees. Right, subtrees. Actually, here's an important question. So let's take this tree. Okay, now that is at some level that's a representation that is more like a hypergraph because it has only one. I mean, it happens to have this nesting property, but it doesn't have this idea. You know, the center dot and the ABC are on sort of the same level. Am I making sense?
Yes.
So the only difference between this and a hypergraph is just the structure of the edges. Go ahead.
I think it's like not correct to look just at one tree ever.
To what?
Like it doesn't. It's like we shouldn't like I don't know, observe any tree separately. Doesn't matter what one individual tree looks like. They can only make sense where you observe it in relation to other trees.
Well, but you wouldn't say that about hypergraphs. I mean, you might say that the instantaneous hypergraph of space is something very ephemeral.
I can say that like atoms individually doesn't make sense without its place in the hyperregion of the whole graph.
Well, yeah, but okay, so what are you claiming here? So you're saying, I mean,
unless you look at the whole pool of trees, any subtree of any individual tree doesn't make sense. You have to like match them up.
okay, but so you're claiming though, these two-way patterns have a top-level operator, which is the two-way rule. And other than that, they're purely structural trees. Am I right? I mean, so in other words, and you're saying that in those trees, everything is a pattern variable. I think that's not going to be right. Maybe it's right.
Well, basically, we have all possible trees. Like imagine, and we enumerated all the trees. That's our pool. Then how we select those trees out is with our rule. Whatever.
Yeah, fair enough.
Modus ponens or logic.
Your point is that, okay, so look.
But what about the TWPs that can only really be produced by predecessor TWPs?
Look, the fact is, what Nick, I think, is saying is that let's write out what this TWP actually is. Okay, this one here. All right, so this one here is, where have I written it?
Lost one parenthesis there. Left.
Why didn't this?
What? Just apply it.
Oh, there we go. Okay, there's the E. Okay, so then we have okay, you're saying just use that on this, which we can. Although why don't we just ignore the equal for a second? Okay, now this becomes what the hell? Oh God, expression tree.
You should something like use health heads
Hold on a
What
second.
is it?
I don't think we need to hold on. That's the issue. The issue is
I think hold heads. Hold everything. Hold.
what? I don't understand this because I just want it to not go inside the blanks. Look, as a hack, we can deal with this in the following way. Whoops. Okay, there we go. All right, that is our relation. So the claim is that thing there is our, and what we need to do it's just a bit weird. You see, because if I start with A here, right?
Yes, you get all of that.
No, that's okay. But I mean, the question is, am I getting the literal O or am I getting a pattern variable O? Am I synthesizing a new atom there or not? You get what I'm saying?
Yeah.
Well, it doesn't matter unless this O is the same across the whole tree. But because we don't like.
Well, let's concretely try to build up logic from this particular expression, right? Because we should be able to do it. What do? We want to apply this expression to itself.
Our rule makes particular pattern O from A. It can make as many as you want, though, but we can just restrict it to make just one O.
I don't understand. All we've got is this, right? And it's saying that whenever we see anything, we can replace it with this whole big blob here, right? So for example, we can just take that expression and we can start off doing derivations in which we just replace a single variable by this. Okay,
Yeah.
and maybe we can start off doing that with O left as a constant.
Okay.
And then later on, we can change that to a variable. But this should generate all the Boolean algebra, replacing A with this, and then applying this rule.
Right.
I think it's tried. We already tried that, something like that.
Yeah.
Right?
Well, I don't know. I mean, I think I've already tried things like this, and I think it works fine. I mean, I think that we should be able to generate from this one thing. There's there's no, our law of entailment is very straightforward here.
It should be.
I think if
Now-
you just do it randomly, or I don't know, just replacing any first found symbol like in this giant tree, it's not gonna reduce very quickly. That's
It's
like
not
the
gonna
first
what?
problem. Because you like if you're just gonna use the right hand side to left hand side rule all over again, you also have to find some different sub-expressions, not that you already just replaced, but some other kind of matching that you can do, can go other way around. And I think
Sure.
if you just do it randomly, it's very hard to find.
I don't disagree, but
So-
let's look. Okay, in here, what I did. Oh, sorry, it was in a previous section. Here we go. Okay, so what this is doing is to apply axioms. It's doing the same thing. Oh, the only difference is, okay, the only difference is it's not generating two-way patterns. It's generating individual results. You see what I'm saying?
Yeah.
The two-way pattern version of that would be, which is a nice symmetrical thing, would be generate the whole thing here, right? Now, I claim, okay, the goal of the theorem prover is to produce TWPs of the form LHS two-way rule true. Okay?
Okay.
In the soup of
Wait,
theorem.
it's just for Boolean algebra.
No, for the general, the goal of the equational theorem prover
Okay.
is to produce a result like this.
The
Okay, so
left-hand side is like can contain equalities and so on. Any propositions.
sure, yeah, can contain anything. The left-hand side can contain anything. The right-hand side can contain anything. Qualities, etc., etc., etc. Inequalities, predicates, whatever you want. Okay.
Mhm.
And when I say true on the right-hand side, I haven't a clue what that actually is.
Do you mean meta-mathematically?
Yeah, I mean,
Yes, I've been wondering that as well. Yes.
right. But the whole point is, that's why in the NKS book, I identified, all I did was to say, if there is a negation operation, it's sufficient to just have a negation operation. But see, I think true requires a further level of interpretation. I think that the relation blah is equivalent to blah, the specific idea that there's a thing called true
Mm.
I mean, it just, you can have it be anything. I mean, it could be, it's just like in combinators, right? In combinators, true, okay, let me remind you how that works in combinators. one of the terrible things about all of this is it's going to turn out that to make the next step in everything, you need to know it. You need to know everything we've known before. Okay, so here we go. So this is true in combinators.
Sounds like a combinator itself. Yeah.
Yeah, but so you see, that's true in combinators. But it's fairly arbitrary what it is. Does this make sense? I mean, that's just saying true is some random expression here. See what I'm saying?
Yeah. Yeah.
And no doubt there are other representations. What's that?
It's true in a sense that not by itself, but that it's true if you use it for all those other operators.
Exactly. Exactly.
Like the whole set.
Right. The whole collection fit together.
Yeah.
But there's nothing absolute about true. What does that remind you of? What about space? There's no absolute space.
Sure.
Yeah. Everything is relative.
Yeah. Everything is defined by relations, even the concept of truth. That's kind of interesting, actually, and undoubtedly correct.
Wow, and it's familiar to people in category theory as well.
Explain.
Well, in category theory, as soon as you use like these like initial objects, like the boldface 1, you have these mapping. I mean, you can express truth in terms of mappings in category theory.
How is it expressed?
With an initial object.
With an initial object 1, and then this, some arrow that has usually the word true over it to another object.
I see. All right, okay. So here's what we need to do here, okay? Okay, so the question is, we've got a really logical problem here. Right? We've got something where basically we've got a minimal representation of mathematics in terms of two-way rules. So now, and this is the minimal two-way rule that we believe represents logic. Okay?
Yep.
And so what we need to do is to build a machine that effectively evolves buckets of two-way rules. Okay, so again, what we expect is we might start from a single two-way rule, two-way pattern, okay? And we then generate a multi-way system of all possible outcomes from that single two-way pattern. Am I making sense?
Yeah.
Okay, so now what we need to look at is, let's take a simple two-way pattern. I mean, so fundamental assumption. Our two-way patterns are operating on trees. Now, it doesn't have to be that way, but it probably is conveniently that way to relate it to mathematics that we know. Clearly, we can
on expressions.
What's that?
They operate on expressions. It's like saying the same thing.
I know, trees/expressions. This could be modeled with hypergraphs, but that's lower level. Hypergraphs may be more convenient for physics. Trees for math. That would be the idea. Because the notion of an operator, what the hell is the notion of an operator? Why is that natural in mathematics? Okay.
It represents action and events.
But it's not an event. The event is the event is the application of this two-way pattern. Look, in physics, we're dealing with pure relations, i.e., one-level lists. Okay, so I mean, I think this may be a matter of, in math, modeling human language, we're dealing with trees. I think that's probably what it comes down to. I don't know if the Babylonians did their math in terms of trees. I mean, this may be a phenomenon of mathematical notation. In other words, this is phrase-structured math. That's what we're doing here, is to say, we're going to, this is what we're going to do to make it vaguely connect with math that we already know. Am I making sense?
Okay.
Nick, does that make sense to you also?
Yeah.
As opposed to the hypergraph case, which is probably going to be exactly the same story. Well, what is the analog in the hypergraph land? Okay, let's do that analog. Analog of TWPs for hypergraphs. Okay, for hypergraphs, it is precisely, it's just a collection of relations. Whatever it is, goes to, rel 3, rel 4, whatever. Okay. Now, we haven't considered the two-way rule case for hypergraphs. We could, but we haven't considered it. And I think what would happen here I mean, I think it's just a special case of sorry, just a second. Okay, so let's look at this for hypergraphs, okay? So let's consider a rule. I don't know, we might consider the rule x blank, y blank, x blank, z blank. One of my favorite rules goes to, I always have to look it up. You know what I'm talking about here?
I think so.
I guess. Yeah.
Yeah.
But the X, Y, X, W, Y, W, Z, W.
Okay, so that rule,
Yeah.
that's our rule. Now, I think there's no problem with self-applying this rule. Okay, so let's just make this rule, okay?
Okay.
So we got this rule, and then we've got its flip around. Okay, now let's put some blanks in here, which is kind of like, and this is something, again, I'm pretty sure that we need some syntactic mechanism, and perhaps we need to make some resource functions to do this, to model this idea of a two-way rule, two-way pattern, so to speak.
Yeah. It's like
And we should
general language design issue.
Yeah, right. Okay, so here we've got this. Okay, so now we say, we now apply that to, for example, this. Let's say 3 steps or something. And
What resource function?
oh, thank you. State plots list. Is that right? Is that what it's called?
States. I think it's plural. States. Everything is plural.
Oh, Christ. This is exactly what I've told Roger to avoid us. And this is exactly this craziness with Max again.
Why just not update automatically?
I haven't a clue. States plots list, is that right?
Is it just states? At least it does work. Just anything works at all, like without any property. Maybe does it have to be rule delayed? Maybe.
No.
It has a problem with that. And it works with symbols, right? And anything. Not just numbers.
This? Yeah, this shouldn't care.
Because I don't remember seeing symbols.
No, this is just some big screw up with, I mean, maybe there's some problem with the structure of these rules. Well, here, let's just try. I'm so sick of this stuff. I'm just so sick of this. Just so sick of this. I'm sure it's a screw up with these stupid. All right, let's try something like this. Let's try this. Let's try seeing whether that works.
Maybe it's patterns, because like you don't have to use patterns. It transforms them anyway.
Oh. Well, that's a good point. Yeah, for this thing, we don't have to use patterns. You're right. This is effectively a two-way rule system to begin with. That's looking more promising. Okay. Well, now I want to see the corresponding multi-way system. Okay, so that's doing the exact same thing, but for pure hypergraphs, right? Make sense?
Mm-hmm.
So now I think we can do the same thing with multi-way system, I believe.
This always applies first rule by default, right?
It's more complicated than first rule.
It's like something maximal.
Yes.
Well, I just wonder if you use that like second rule as first, it shouldn't
I see.
evolve at all. It would just go back and forth.
Oh, for God's sake. It's just unbelievable, this stupid thing. If I abort this, it's going to just abort everything. Oh my God, it just crashed the whole thing.
Even worse. Oh.
Well, let's try running a different version. But I think we're onto something useful here. I think this is a good way to think about it. I think what we've got here is, you know what I'm saying? I mean, I think we're understanding what is the minimal version of mathematics that is vaguely understandable. And it's very close to the hypergraph thing. It just involves some tree structure as well. Am I making sense?
Right.
Yeah. Yeah.
But now, let's just check that it still works. Oh, come on, don't give me that nonsense again. That's just so stupid. Just so stupid. Okay. Now you wanted to see what happens if we reverse these.
Yeah. Okay.
Okay.
Well, here, why don't we do this?
I think there's an option.
No, I was going to look at this thing here. Okay, and now let's look at the one with the thing unreversed. That is odd that those don't give different results. Well, let's see what happens if we just remove the second rule. Huh. It never fires. That's really odd that it never fires because it must be generated. You get what I'm saying? Maybe it's always shielded for this evaluation order.
What if we try some event order function?
Yeah, I know. What event order?
I don't random or
I think random is not going to be so useful.
newest stage or oldest stage.
Okay, so how do we do that? You see this thing, arrow newest edge, is that right?
I don't know, there's a event ordering function option. I'm not sure about just our orientation. Event ordering function.
Nearest edge, is that?
Yeah, newest edge.
Well, that wasn't very profound.
So this is, yeah, this is what I expected it to. Just create, destroy, create, destroy. Always the same expression.
Yes, okay, fair enough. Because it's just going back and forth. Right, with this foliation, it just alternates back and forth.
Oh,
So now we
rule ordering, like event ordering function, rule ordering, then it's gonna use the same order that you specified it. So that would make sense if you reverse it, the list. And without reverse, it's going to be back and forth, I guess. Maybe not.
Oh, it seems to be exactly the same again now. Well, okay, but let's try looking at the multi-way system here. Actually, let me just do a parallel. It's just so crazy. What it basically is machines being woken up so that SSH works. Do you get what I'm saying?
Yeah.
It's crazy. It's just absolutely frigging bonkers. I mean, the operating system surely can deal with having a woken up SSH. Something needs to wake up the SSH.
You mean like persistent connection?
Yeah. Well, I don't know whether it's a persistent connection, but whatever I'm doing twice to wake up the SSH, we could just do. You get what I'm saying?
Right. Yeah. I don't see a problem. That should work.
Yeah. Just bonkers. We could take a simpler rule here, but okay, great.
Is it like connecting or also launching kernels there?
It's also launching kernels.
Launching kernels should take longer. I think that's
okay. So let's take this and we say Wolfram model arrow that, if I remember correctly. Is that the right way around?
no, that's correct.
We have got to rewrite multi-way system. Okay. And then let's try with this. Let's say 2 steps. Then what is that creature? Well, let's just do a states graph just for the hell of it. States graph. Huh? What do you mean there's nothing there? Oh, Christ. Okay. Oh, maybe we have to put that in an extra level of list.
Mm-hmm.
And we have to say vertex size.
Mm. Mm.
Okay, so this is showing us for this rule. So if these were mathematical expressions, there's one difference here.
Mm.
You see, this is evolution. We're not doing this accumulative evolution of two-way rules. We're just taking these hypergraphs and we're evolving them. So what I'm saying, this isn't learning, you know. this is an unlearning system. You see what I'm saying?
Okay.
What does it look like if the if there is, quotes, learning in the set of rules? You see what I'm saying?
Well, maybe let's parse out what you mean by learning, just to be.
Well, I mean, what I mean by that, i.e., from a rule,
Yeah.
we derive another rule by evolving one of the sides of the rule. You see what I'm saying?
Isn't it just a matter of interpreting your hypergraph? Maybe you interpret one set of hyperedges as a left-hand side and another
Sure,
as a right-hand
absolutely. Yes, you could do that. But the point is, the way we're drawing it, we've got these big hyperedges, right? Whereas in this case, we are, so I'm saying what we're going to do is we're going to say, 2, 3, 5, 2 goes to blah, blah, blah. Let's say 2, 5, 3, 3. Okay. And then we're going to transform that.
Yes.
And we're going to get from that a new rule. Do you get what I'm saying?
Yep.
Which we can then use again.
Yep.
Okay. And that's the difference, because what we're doing in the physics case,
right,
is we don't have that notion what is the difference really? We've got, in the math case, these rules are kind of allowing us to jump around the space of mathematical expressions. Whereas in the physics case, see what I'm saying? This is inducing transitive closure, basically, here in the math case. We're saying if this is equivalent to this and this is equivalent to this, we're going to make a direct rule.
Yeah.
Can you actually encode it, this kind of behavior, into a hypergraph? You can just say that one particular atom acts as a two-way rule, like one. If it's like at the beginning of your hyperedge, then it's like what follows is the like hyperedge, well, left-hand side and then right-hand side. Or maybe what follows are atoms that are starting the hyperedges, that means left-hand side and right-hand side. So you can basically encode trees with hyperedges first, then just do the same.
Okay, explain.
Just a scheme of encoding trees with hyperedges. That's it.
No, I know. But we're doing more than just trees. Remember, because we've got two operators here. We've got trees, and we've also got, I mean, just encoding this kind of thing, this transformation. Yeah. See, the difference is, In the physics case, we imagine there's a single rule, and we just keep on applying that rule. In this case, we imagine that rules are being built up that we can then apply.
Right. It's more rulal in the mathematical case. So when you say learning, you basically would like for the graph to include the history of the development of these rules over time.
Rule is also a tree. So
Yeah, I know. We can encode that, but the point is that the rule of inference is more rulal.
Yeah.
There's more flexibility in the rules than we imagine there is in physics.
is it? It's like, no. I
What's
think you just add some kind of additional rule to parse this rule, and that's it.
Okay, explain.
Or something like that. So it seems like you still can. I don't see a problem why it's impossible to encode this rule into hypergraph.
It's not impossible to
Oh,
encode.
no, it's
No,
not.
it's not impossible to encode it.
It's
The
just
point
different
is what
from it's just different from physics. I mean, imagine if in physics we were having different laws of physics producing, additional new laws of physics for some model for explaining physics in our universe. That would be quite strange. But in mathematics, it's different.
right. In other words,
It
the
depends
progress
on
of mathematics. Go ahead.
it depends on what level of physics you're looking at. Maybe it's like the whole multiverse is encoded like that, but not our particular universe with our particular laws of physics.
Well, that's an interesting question. Whether there is a view of physics. Basically, it's the hashed view of physics in the following sense. Everything that's already happened in physics, right? It's as if there's a view of physics. Okay, here's the difference, comparison. In math, every relation that has been discovered is used forever, is used anytime in the future. In physics, ordinary physics, things happen again and again. They are not cached. Right, but so we can essentially imagine a transitive closure of physics.
Well, maybe like hyperedges that represent laws of physics are cached.
Yes.
Yes, I mean, my interpretation of Nick's point is that this is a meta mathematics project, unlike the physics project, which is not like some, I don't know, metaphysics project. We're just looking at it slightly differently.
Right. We can imagine a transitive closure where everything that has happened is cached. In the ordinary model, only the underlying rules are cached. So what you're saying is we can view in the Roolead, we could do this kind of caching for the Roolead if we wanted to.
I think it's like in Roolead everything is cached, but whether we cache in our atoms of space is like the part of the laws of physics rules. Whether they're cached or not, it's like their problem. Maybe they were assigning some kind of IDs or whatever, time or whatnot. But it's like different levels. Roolead caches everything. It's like exactly as mathematics. But
when you say it caches everything, the whole idea of what we're talking about in mathematics. See, okay, this is the confusing part.
Oh, yeah, right.
This is the confusing part. The confusing part is, in the Roolead, we start from everything. But what gives the Roolead structure is the fact that there's entanglement in the different things that everything leads to, if that makes sense. So
you're saying the Roolead can't cache anything. It's already the cache, the pre-given cache itself.
No, I think a way to put it is, look, here's the point. The caching in the Roolead, okay, can be viewed, okay, caching in the Roolead, okay. The Roolead involves all possible rules. But given a particular point in the Roolead, it takes time to reach other rules because you have to build them up from your local rules. So I'm saying, but they are there somewhere. But to get to them, you have to essentially go through time and build them up. I claim.
And that might feel as though you're caching them in some way, but it's not as though you're caching them in the Roolead because they're already there.
Yeah, they're already there.
You're already kind of tracing what's already there, though. For the observer, it'll feel like you're discovering something.
Yes.
Yeah. Okay.
The thing that's confusing about this is that our view of computational irreducibility tells us that the statement "it's already there" is a very Chaitin-esque infinite statement. See what I'm saying?
Mm-hmm.
In the presence right, it's something, it requires, it's something super computational, so to speak, to say it's already there. And by the way, and it's not accessible by a computationally bounded observer. Oh yeah, look, here's the point. Here's the point.
Mm-hmm.
The point is, if you're in the Roolead and you start at some point in the Roolead, okay, to reach another point in the Roolead, you have to actually do computation.
That's right.
And if you are a computationally bounded entity,
that's right.
It's going to take you time to do that.
Well, that's the point of computational irreducibility.
Yeah, but I mean, you can't move around in the Roolead, just like you can't move around. And so that also is a statement in mathematics. What's the analog of that in mathematics? The analog would be, yes, there are all these rules sitting there. Oh, I see the difference. I see the difference.
The Roolead is like such a thing that even with all possible rules, there is, even for infinite number of all possible rules, there's not such a rule that takes you anywhere in one step.
Saying there isn't. What's that?
Yeah, even with infinite number of all possible rules, you can't reach anything with just doing one step.
I think
There's
you
no
can
such-
eventually. It's a question of orders of infinity, I think.
But
There's different limits.
The point is, though, that the Rule-Iad is all possible rules, but it's not.
Yeah.
Thinking of it as all possible computations is kind of a funny thing to say. I mean, computation is ultimately the navigation of the Rule-Iad by some sort of computationally bounded observer, right?
Yeah.
So if we're speaking about computational irreducibility, we can't speak about the Rule-Iad in terms of that, but we can speak about observers in the Rule-Iad as experiencing that necessarily, because they're bounded computationally within this space of all possible rules.
Right. And I think the difference is mathematics textbooks are long, whereas we're imagining, in other words, our human cache. Okay, the difference between math and physics. Here's the difference.
You already had this title just now.
Oh, well, anyway, okay. Comparison between math and physics. Well,
The real difference between yes,
yeah, right.
math and physics.
Is that in physics, we imagine that there are a finite set of underlying rules. In math, this is actually very interestingly screwy, because in math, we imagine, yeah. This is actually directly analogous. There isn't a problem here. Okay, finite set of underlying rules from which we can derive everything. But we could have cached higher level rules. In math, we imagine that there are a finite set of axioms from which we can derive everything. But we like to have higher level cached lemmas. Now, the thing which is interesting and different is
those sets are not unique.
no, they're absolutely not unique. In fact, you could start from anything. I mean, basically, PCE, oops, that was not the right thing. PCE implies that you can start from essentially any set of rules in both physics and math.
Okay.
What then matters is the relation of the observer to these rules. Okay, so in math, let's say we start from the axioms of geometry, but we're going to do number theory.
Okay. Yeah.
It's a perfectly
Actually,
reasonable thing to do. Go ahead.
It's like, do you think it's like, that's why we have this kind of useful math theorems, just because we have particular laws of physics, because they are related in this way.
Let's understand that claim. Okay, try that again.
So just because we live in this universe with particular laws of physics, with particular set of laws, right? We tend to invent or discover mathematical laws that directly related them, or even equivalent.
Yeah, that's an interesting.
But it could be the reversal, though. It depends on what you feel is more fundamental.
Yeah, they're kind of, it's a loop.
Yeah, right. Are the discovered laws of mathematics based on the discovered laws of physics, or the observed laws of mathematics based on the observed laws of physics?
Or
So, I mean,
vice versa, or vice versa.
Right. Okay, but the basic point here is, this is basically the statement, the universe is a Turing machine. Both of these are basically just that statement. You can start from anything. The issue is, how ornate does the observer have to be? You can have a more convenient basis that lets the observer be simpler, if that makes sense.
What do you mean by basis?
Well, I mean, you don't start from a Turing machine. You start from some hypergraph rewriting thing, rather than starting from a Turing machine, which is ultimately equivalent.
Okay. Yeah, okay.
Right. And so in mathematics, we might start from this tree-based axiom thing, just because that is a more convenient thing for the mathematical observer than something else. Even though we know perfectly well we can build. Right, but the issue now is, okay, so the basic point is, we could build all of mathematics from its axioms, and every time we need to know anything, we go all the way back to the axioms and rederive everything. Right, that will certainly work. And the claim is that we can go all the way back to essentially any set of axioms, but the stuff that we will derive this is basically a Rouliad type point that basically we can, or it's a PCE type point that we can always. The basic claim is that the structure of mathematics is always the same. It is merely the interpretation of the symbols that gives you number theory versus this versus that. That's the basic claim.
But I don't think we've answered why we get this mathematics from this pool of all syntactic statements yet.
Well, we have. We've answered that mathematics is the structure that, but to interpret, and that's what we have to see. What we have to see is that there's a projection. Okay, what do we need to do? It's just like analogy. Given a random universal Turing machine, we can make it emulate whatever we want. Okay, so now what we have to do is, given a random, tree rewriting system, we can make it emulate some area of math. See what I'm saying?
Interesting. Yes.
And so axioms and their typical laws of inference are just one possible basis for math. Any computational system is also a basis, is the claim. And the basic claim here is, given that fact, the bulk limit of this kind of multi-computational thing, oh boy, has certain properties. The reference frame that we as computationally bounded observers can pick out from all of this has to have certain properties, is the claim.
But why do we have the reference frame that we have?
Because of the history of mathematics. And because of what our brains can untangle. we can imagine alien mathematics. I've been thinking about this whole reference framey type thing, and it's really kind of interesting because, like let me give you an example, which I think somebody who wrote into us has mentioned. Okay, imagine that you are a non-neurotypical human. Okay.
Okay. We're gonna try very hard. Yes. Okay.
Okay. You have a different view of the world. In fact, one might even argue that every individual person has a different view.
Well, that's what I was implying. Yes.
Right. Everybody has a different view. Everybody is operating in a slightly different place in rulal space. And there is a translation. One could imagine if one could do brain emulation, one could have translations between them. And there will be a certain distance between different people's, internal sort of processing. And what's interesting about that is that it kind of makes the point. It's a very anti-modern Western science point, I have to say. Because it suggests that there are potentially quite different, even human accessible reference frames. I also think, okay, so here's another outrageous claim. When augmented reality is common, we will find new reference frames.
You need a set of orthogonal reference frames.
What's that?
We have to I don't know, strive for more orthogonality in reference frames.
Well, perhaps, but I mean, look, the point is that we base our experience of the universe and our laws of physics. So there's another important point. Okay, if you look at the history of science, right, there are things about which there could not reasonably be laws until we had ways to detect them.
Sure. Yes.
Right?
Yeah.
And we didn't have, and right now, for example, this potential new interpretation of chemistry, right, in terms of causal graphs and God knows what else, right?
Mm-hmm.
There may be general laws of chemistry which become accessible if we manage to find ways to detect causal graphs in chemistry.
But they couldn't have been identified without those tools.
Right. That reference frame is just not one you can construct. In other words, the construction of reference frames is like what instrumentation is available in science.
Right.
I mean, in fact, what this is doing, okay, in fact, this is very interesting. This is very interesting because the idea of instrumentation in science, one knows very well that the history of science is driven by advances in instrumentation.
Yeah.
This is a science of the progress of science in those terms.
Yes.
This is saying what is the mathematical interpretation of the advance of instrumentation, right? So in other words, what this is saying is the mathematical interpretation of the advance of instrumentation is different reference frames than the Rulliad, basically.
The question is, does it allow us to augment our own reference frame, or are we adopting a different one?
I don't know.
I mean, in the end, we're fashioning our own instrumentation. This is where you see. So we're fashioning it, but in some ways it's inhuman, but in some ways it's just an extension of our own
Well,
capacity.
but look, modern science, the reference frame available to Aristotle is different from the one available to us today.
Yes, but it could be. I mean, if he had the equipment, if he had the instrumentation, he would share the reference frame. So it could simply be.
It might not be the case. It might not be the case.
What?
Because his brain and his conceptual development and, ambient understanding might be different.
Your brain
have
is
to have-
also an instrument.
Right. But not only the brain, but also the cultural knowledge that goes in there.
That's your brain. So
Indeed.
brain and environment.
Right. But I mean, that's the point.
Well, I was going to make the claim that observers, there's no guarantee that an observer has full access to the available breadth of their reference frame, right? But with instrumentation, accessibility of the full breadth of your reference frame, grows. That's kind of how I would look at it.
Possibly. I think it's that there are slices of the Rouliad that are just not available. I mean, the classic case, which I keep on coming back to, is the detailed motions of molecules in the air.
Yes.
Simply not accessible to us today. And it's not accessible for many reasons, right? It's not accessible because we don't have the instrumentation to pick up the motions. It's not accessible because we don't have a description language for it. We can't turn it into something our brains can process. Even if we could detect, it's like a neural net, right? In a neural net, we can perfectly well see everything that's going on, yet we have no way to describe it, to process it. We have no way to brainify it, so to speak. And I mean, arguably, the whole computational language thing is in some level a sensory extension process.
Yeah.
Another instrument.
Indeed.
A very powerful one.
Right. But I mean, the question is, in the Rouliad, in Roulial space, it's very big. And we are exploring but a tiny, tiny corner of it. Just as we're exploring a tiny corner in physical space. Not even to talk about branchial space, which is a whole different can of worms. I was realizing that Roger Penrose's objective reduction stuff, I don't know whether he realizes, maybe he does, is the analog of black hole formation in branchial space.
Yeah.
In our models, right, the concept that in branchial space everything converges to a definite value, that is a story of black hole formation. That's you reach a normal form in branchial space. I mean, I think it's kind of an interesting. I'm now.
But that's just reducibility, though, as well.
Yes, but the fact is, what he's claiming is that there are physical processes that lead to objective reduction, which I've always thought was just nonsense. But I don't think it is. I think it's actually an interesting perspective there. I mean, we don't really know much about what happens in branchial space.
Oh, but I mean reduction, not in their sense of reduction. I mean, we usually, at least in the physics project, we speak of black holes in terms of computational reducibility. And I don't know if reducibility and what they're calling reduction is really the same. It might be a more kind of nuanced description of it.
It is the same in the end. It basically says in branchial space, different observers who might be following different paths in branchial space are actually all converging to a single normal form.
Yes.
It's the same thing.
Now, another note on on the reference frame question. You see, what I've been hoping for is at some point that we would take this pool of all these syntactic statements and we would be able to, in this map, even though it's not going to be possible to represent a very large graph just visually, computationally, but nonetheless, starting with something very, very basic, basically make it possible to illustrate our reference frame, show how our reference frame emerges from others,
that's what we
how
want
it's
to do.
distinct from others.
That's what we want to do.
So that's still the goal. Yes.
Yes,
Okay.
that's
Good.
the goal.
Okay.
The goal is to extract logic from a sea of all possible, from this sea of to start from something, basically to find what we want to do is somehow to start off with a random, arbitrary. I mean, it may take a little bit of effort to find a universal one, but it probably won't be too hard. To start off with some random
TWP, right?
Yeah.
Well, and hopefully, as we were saying before, hopefully this kind of pruning characteristic of TWPs, so long as it prunes fast enough, then we should be able to I shouldn't say we should be able to, but it'll make it possible to find our reference frame if the pruning happened at a sufficiently kind of fast rate.
Look, basically, okay, let's draw the analogy with physics. Okay, in physics, we have the very lovely fact that it doesn't matter which underlying rule we took. We still get general relativity in quantum mechanics. Okay. The question is, it should be the case. Okay, we get general relativity in quantum mechanics with certain rather coarse assumptions about our reference frame. You see what I'm saying? We don't need very detailed assumptions about the reference frame. However, it could very well be the case that to get logic out of the sea of all possible mathematics, we do need a rather specific assumption about our reference frame. It could be.
But what do you mean by an assumption?
Well, I mean, some detailed way of picking the reference frame.
Well, good. Yes.
Right. But see, but the fact is, it doesn't matter much. In physics, we still get general relativity. Even if we have, we can have many different reference frames because general relativity itself talks about many different reference frames. You see, here's what's going to happen. Here is what's going to happen. Axiomatic mathematics is going to be brittle with respect to reference frame choice. But mathematics as practiced by mathematicians will not be. That's what I think is going to happen. And so my assertion about this is that at the level of the concepts that mathematicians care about, we already know that the detailed axioms don't matter much. Actually, they don't even matter in proving a given theorem.
Well, this seems testable. And this actually seems like a way of testing this whole idea of the continuum limit or the fluid dynamics versus the molecular dynamics of mathematics. So we start with arbitrary, I almost said PWTs. We start with arbitrary TWPs. And you're saying we should be able to find mathematics for the working mathematician, but we might not necessarily find axiomatic mathematics. You might have to be more constrained, or you have to have stronger assumptions, or just desiderated for the reference frame in order to get those. Well, we could compare those, and then we could. I mean, if that's the hypothesis, this seems like it could be testable. But I mean, so what I've been worried about is that this will be some difficult brute force test. But you're saying that it shouldn't be. You should just be able to start with some arbitrary TWP.
Well,
there
something like that. Yeah. I mean, I just think we need to actually be able to get the minimal TWP, self-generator. You get what I'm saying? Just like we have this self-generator here, right?
Yeah.
But this is not the transitive closure self-generator. We need the minimal TWP transitive closured self-generator, which shouldn't be too difficult to write. And we should do it both for the pure relations case, i.e. hypergraphs, and for the trees case. And
have to put some constraints on it in order to, I think like the actual axioms that mathematicians use gonna arise when we constrain our generation, like with some kind of notion of complexity. Because like a Wolfram axiom, it's kind of, I think, will produce very complex expressions. That's why it's not very useful. But if we
but you're not right that it isn't useful. It generates Boolean algebra. Boolean algebra is just fine. It's not even terribly inefficient at generating Boolean algebra. But that axiom on its own, if you look at it at the molecular dynamics level, is horrifying. Right? But the mathematical structure it generates is just fine.
It's fine. I'm not, it feels like if you just say, put a constraint to extract from simple two-way pattern rule pool or whatever of patterns, to extract those that have like minimal depth.
I see what you're saying.
It will extract those axioms that are actually used by mathematicians and not the Wolfram axiom of Boolean logic. That's gonna be only when we like loosen up some constraints.
Yeah, okay, fair enough. I mean, your claim would be, well, your claim is, which might or might not be correct, that the reference frame used by working mathematicians, I'm not sure it's correct. I think that is like saying, in a gas,
don't use very deep trees.
Yeah, but I think it's like saying in a gas, I only want this collection of microscopic collisions, which is absolutely not what anybody would say. Right? Instead, what they would say is,
no, that would mean we don't like take into account free, how do you call it? Free collision of free simultaneous molecules like that. Yes. And more. Even there is a possibility of them happening, but we ignore them.
What's your point about that?
I'm not sure.
Okay. Okay, but look, practical matter here. What we need is, what is the minimal, minimal TWP. I'm having a hard time with PWT, TWP. Minimal.
It's not theories with persons.
The minimal TWT generator case 1, hypergraph-like relations. Case 2, tree structures. Okay, so in the case of hypergraph-like relations, what we're trying to do is we're trying to say, this collection of relations goes to some other collection of relations. Yeah, it should be pretty straightforward, right? I mean, it's just like saying, it's just like subset replace, isn't it? Okay, so how does subset replace? Okay, so what we've got, okay, so let's do case 1. So we've got some list of rules. We've got blah, blah, blah goes to whatever it is, okay? Got something like that. So the fundamental operation is, it's basically a two-way pattern. Yeah, it's just take pattern 1, pattern 2, and we're going to generate pattern 3. And actually, this is, this is a pattern combiner, pattern applier. But it needs more information, right? This says, because there are many possible places, location 1 and location 2. No, it's just location 2. In what location of pattern 2 is pattern 1 applied? Is that correct?
Yeah. If you want
Okay.
locations, I still believe it's not, you not necessarily need them. If
You think you can do it at the top level?
Yeah, if you construct all your expressions from scratch anyway, so all those subparts are available to apply your pattern.
Right. Okay. So let's try it then. Okay. So we're saying that these. No, it can't be right, because in a hypergraph setting, we're not updating the whole universe with one hypergraph rule. You see what I'm saying?
What we are doing.
Well, we're taking a sub-hypergraph. We're updating a sub-hypergraph based on, right? I mean, this pattern applier could apply it to all possible places. So let's just take the example. Okay, so what this is going to do, it's going to ask, in the original hypergraph, what are all possible places where this is, I mean, again, this is something we've okay, 1, in the original, in pat 1, which is otherwise known as LHS1 goes to RHS. Well, let's say LHS1 goes to RHS1, okay? So in pat 1, where does LHS2 from pat 2 apply? That makes sense? And then we want to create pat 3 from all possible such rule applications. Does that make sense?
Not yet.
Okay, so what I'm saying is the pattern applier is
Yeah.
applying pat2 to pattern 1.
Yeah.
Okay.
Right?
Mhm.
And that what it's doing, so what does that mean to apply pat2 to pattern 1? That means in pattern 1, which is of the form LHS1 goes to RHS1, I should have said there, where does LHS2 match? Where does it apply? Wherever it applies, do that replacement. You get what I'm saying?
Yes.
It's just
And
in original idea just of pool of patterns, there is also LHS and RHSs kind of floating around separately from the rule 2.
I'm sorry, say that again. In the pool of patterns, what were you saying?
There is not just patterns of the form left with like arrow, right? It's also LHS and RHS also in the same pool. That's why you can apply your pattern to either to the left hand side or right hand side separately, and then reconstruct this rule again.
Well, that's a question of what the I mean, you're saying there are two kinds of things in math. Are there, in fact, two kinds of things in math? A, expressions, and B, rules. Because that's what you're basically claiming.
Kinda, yeah. It also like in category theory have like exponential objects.
What do you mean?
Yeah, exponential objects is like objects that basically encode your morphisms from category 2. So if you have a morphism from A to B, and you have exponential objects,
E to the A.
that you,
Yeah.
it's like function. You also have, it's the same way as saying that you have in type theory you have function of type of functions, not just arguments of functions.
So instead of instead of 2 to the n, you can also just have mapping n to 2. And then you can represent that as exponentiation as 2 to the n.
Yeah, basically function type.
But this is good. This is because in category theory, sums and products, you represent them all in terms of morphisms in these different relations.
What's the difference in the rules that we're describing now? Why isn't expressions, objects, and rules morphisms?
Expressions, objects, rules, morphisms. Well, morphisms, in the end, here's the thing, morphisms can be treated as objects as well.
I know that.
But objects can't necessarily be treated also as morphisms unless there's some sort of morphism.
Yeah, exactly. But that's the same situation we have here. We've got an expression, and the expression might happen to have head rule, or it might not.
Well, I kind of just convinced myself through category theory to agree. But wait, does Nick disagree with that?
With what exactly?
The objects, they're expressions and rules, although rules are a special case of expressions, and that's the analog of objects and morphisms in category theory.
Yes.
What's the analog in type theory?
that function type is just a
Type.
type, right? You have type
So
for
okay. So
argument.
in type theory, the analog is functions. No, it's just types, general types, and the function type. That's the analog, right? That there are general types like integers, and there's function types, which conveniently are usually represented with arrows. I mean, basically,
Yeah.
all three of these representations use arrows for this case,
Correct.
which is
They're useful. Yeah, arrows are useful.
all of these representations happen to nowadays, because functions didn't always do that, use arrows for the rules / morphisms / functions. And you know, a C declaration doesn't use an arrow for the function type. Okay, so we're concluding that there are two kinds of things which can be conflated, but only with a certain degree of messiness. And now we're saying, you know, essentially what we want to do is enumerate. I mean, it's like enumerating category theory. Why don't people do that, by the way?
Do what?
Enumerate possible categories.
Enumerate possible categories.
I think they do. It's like if you have one object, then you have, if you put multiple morphisms on one object to get monoid. If you get two objects, what kind of categories, then you can have, and so on. I think they have.
Well, what's the answer? I mean, so in other words, that would be useful to know, because this is, in a sense, we might build things up. We might minimally build up math just as category theory does. I mean, assuming that we have only, but I mean, you know, so for example, let's say we have only one type of atom or something, then we probably have some particular setup here. Okay, but what we have to do, so we now have a pretty clear thing. We need to write the pattern applier. I mean, this would actually be pattern apply of
Why it's not just modus ponens as I had before?
I think it's pretty close. Let's look at your modus ponens. Oh God. Max's code defines a token event graph function.
Yeah.
That overwrites this one. Oh, what a mess. I'm so fed up with this stuff. Okay, in any case, your modus ponens, what does it actually do here?
So it takes a rule and a pattern, right? which in this case particularly all but rules, but it's not necessary, right? But only when like right hand side matches to the left hand side of your rule, right? Only those kind of, yeah.
Well, okay, but how do we write this? I think we're going to write, as a practical matter, we're going to want something which doesn't depend on, which doesn't require pattern variables here. And it's just a detail. And also, we don't need the tree. You know, there's a few other details here. Right? We want these things so that the order doesn't matter of the hyperedges, for example.
I don't think it actually requires pattern variables.
Okay, so give me a function. Okay, can I write pattern apply in terms of your thing? How do I do it?
I guess just to replace it.
This here. Is that right?
Well, maybe. Or maybe just the replace part, because this is for token length graph, so it also copied over rule and the left hand side.
Okay, so there's pattern there. And what's left-hand side of the rule is just, first of all, here, let me just write this as LHS, arrow RHS. Right?
Yeah, maybe.
Okay, so let's try this then. So then we say pattern apply. I don't think this can possibly work because of the orderlessness of the outer wrapper.
That's why this rule was a part of token length graph. It didn't care about order. Token graph picked out two things from the pool that match this particular pattern.
I see. Let me just read in my token event graph. Oh, for God's frigging sake. This is really annoying. It's really annoying. We really need to get this submitted like tomorrow into the function repository so that we untangle this piece of idiocy.
I can just submit it.
Nick, you think it can be done?
Okay.
Nick, you think we can publish it? You think you can publish it tomorrow?
I wonder if I specify publisher ID Wolfram and publish it like with it. Is it immediately gonna be like available? I think that's how it works. I'm just gonna try. Okay.
Do you know if that would work, Stephen?
I have no idea.
Okay.
So you're saying that in token event graph, well, you're saying we actually have to use the modus ponens rule.
Yeah, that was the idea. And also some logic.
Well, okay, this is getting more complicated because we want the absolutely minimal thing. We're just trying to, let's try to just, all we want to do is like origin of life. You know, we got these bubbling abiotic things and they're gradually going to combine with each other. And, you know, does an amphibian walk out, you know, a billion years later? You know what I'm saying?
Yeah.
Because what we should see here is something where we have what we want is a multi-way system, multi-way graph, Oh God, is that really what we want or not? Yes, is a multi-way graph whose states are complete lists of TWPs. That's very inefficient. That's a very global multi-way system. Okay, that object there, these states, those states are states of mathematics. With certain proofs having been done.
A multi-way graph whose states are complete lists of TWP.
Sorry. Oh no, are complete lists of TWPs.
Yeah.
Those states are states of mathematics with certain proofs made.
States are those pattern pools.
Say that again?
That's the thing. Not all the TWPs actually make their way into our mathematics, though.
Which don't?
What about those that aren't in our reference frame?
Yeah, well, fair enough. We're not going to care about those. But the whole point is this is making...
Okay, I'm just making sure. I mean, if
right,
you
there's multiple pieces of filtering going on, just as there is in physics.
Okay.
One form of filtering is the time evolution.
Yes.
By the way, I do think that this Rullial reference frame point of view thing, I have this feeling that it slices through a huge number of historical mysteries in philosophy. Interestingly enough.
Well, unless you want that to be a somewhat enigmatic remark, you'll have to mention at least one mystery that you're thinking of.
Yeah, I mean, all these things about the relationship of humans to the universe and all these different theories for whether we generate our own reality or whether there is reality out there and we perceive it and so on and so on and so on.
Mm-hmm.
Because what this says is we're all in our own Rullial reference. We're all in different places in Rullial space. So in some sense, we all have our own reality. But in some sense, we all live in the Rulliad. And there is a translation that we can do between each other that is a Rullial piece of Rullial motion.
And then it's relatively inexpensive.
Yeah,
computationally.
we're
not that far apart.
Humans to humans, we're not that far apart, but humans to the weather, we're pretty far apart.
Yes.
It's hard for us to simulate the weather. It's hard for us to empathize with the weather. You know, the only medium we have for simulating the weather is computers. And there is an irreducible computational distance.
Yeah, that is, I mean, it's nuanced because it's neither solipsistic, nor is it making these kinds of claims about humanity as a whole that are kind of difficult to make.
Yeah.
And
yeah,
it feels about right.
Yes, I think so. I mean, it both explains why there is a common reality, because it's basically computational irreducibility in Rullial space. Computational causal invariance in Rullial space. The fact that these different paths in Rullial space wind up being consistent. Oh, it could be the case that two people trundling along in different directions will never have consistency. They'll never reach consistency in their view of the universe. But this implies that they will.
Well, and it also kind of helps to explain the kind of, well, I don't know if I'll say explain, but you can also think about the kind of Kuhnian view of normal science and how, sometimes even destructively, we create these traditions in science that sometimes seem too rigid and inflexible, but maybe to some degree, it's actually kind of remarkable that you've managed to come up with some way in which people who have slightly different reference frames can nonetheless contribute at some high level to some shared project.
Yeah. But you see, I think the thing that is really, I think the real takeaway from a lot of this stuff is, one thing which is kind of obvious is the science we build depends on what we can measure and think about.
Well, yeah.
And, we might imagine that current Western science is the king of the hill, so to speak. But we're probably wrong. I mean, not relative to what exists today, probably, but relative to what could exist.
Well, it's not surprising to hear you say that, though. I mean, NKS, you published NKS over 2 decades ago. So
yes,
it's not the first time you're making this argument.
Well, right, but in a sense, what's the role of ruleology? I mean, okay, look, you're right. The computational telescope analogy is kind of seeing into a different part of rulal space.
Yes. Yes.
You can market your language like
that. Yeah, but you see, but what we have to do, the thing that's really, really bugging me here is that here I am about to try and construct this symbolic discourse language that takes current human thinking and encapsulates it computationally.
We haven't discussed this project in a long time either. So just for my own preparation or just the context, where is this on the priority list? Because it hasn't been mentioned since I first started in August.
It's just not there because basically what's happened is it was the thing that I would have done if the physics project hadn't been done. So it's been displaced by that. But it's, I mean, and look, I think the basic point is, I think the order of things is this mathematics stuff, the Rulliad stuff, although I'm concerned that I have to write something about the Rulliad before I can explain mathematics.
Wasn't it? I thought the order was reversed. At least it was reversed.
Which order? The order when?
Well, basically, in terms of the ordering of these projects, let's make some advances with mathematics so that you have something to say about the Rulliad.
Yeah.
I mean, they're deeply intertwined. They're deeply interrelated. I imagine
order depends on your reference frame.
The Rulliad will kind of make these kind of Albert Hitchcock-like cameos in all the essays, right? Because the Rulliad makes everything, and so it shows up. It shows up in all the works as well.
Sorry, say that again. I got distracted by something. Could you repeat that?
Well, no, I was just making some quip about the Rulliad will make these kind of Albert Hitchcock-like cameo appearances because it makes everything, and so it will inevitably also appear.
Yes, I see.
In some way. Yes.
But you see, the thing about the Rulliad is I don't yet understand. It's like the sort of Chaitin-esque view of everything is in the Rulliad, but not near other things, so to speak.
Not near other things.
Well, I mean, what I mean by that is, if you want this particular ornate rule, but you're sitting in a particular place in the Rulliad, you have to do, irreducible computational work to sort of, iterate your way to that place. But I'm still trying to understand how that all works. Oh, gosh. And I would like to have some better models of the Rulliad. I mean, we have the multi-way Turing machines. We sort of have the strings case. I don't know what the good models are for it.
Well, it depends on what you mean by model. I mean, we couldn't model the Rulliad in full, obviously.
No, but the question is how to get intuition about it.
Well, we have intuition about it.
Yeah. I mean, look, okay, the current things that are on my, there's the Rulliad stuff. There is talking, the intuition about branchial space, which is getting ever better. And then there's this correspondence with the history of philosophy project. Then, of course, the Rulliology projects. Then there's the infracalculus project, which really needs to get done. The symbolic discourse language project. I mean, look, the beginning of that project is comparatively straightforward. It's basically take a thesaurus and start encoding its content in computable form. And it's a calculus of, A, transportation verb B, I walk from A to B type thing. Okay, if that's the case, what does that mean? What is, if you walk from A to B and you walk from B to C, does that mean you walked from A to C type thing? There's a series of kind of calculi that operate around different kinds of meta concepts about how the world works. And some of these have been encoded. People have written encodings for them in various forms of modal logic or whatever else, and many they have not. And I don't think they're very hard, fundamentally. They're mostly very straightforward, common sensey type things. The point is to have a, the concept is, just like in Wolfram Alpha, we didn't start Wolfram Alpha by having a theory of the world. We started it by implementing particular kinds of subdomains. And then we gradually ended up building up to a broader theory. This will be the same way. And
it would be very useful to solve abstract reasoning problem.
Of course.
There's like a set of challenges that I think still not solved by any machine learning technique.
Indeed.
And people are like encoding all those rules on how to think about it, because humans very simply can think about all those problems to the computer.
Right, but the fact is it's just like, you can go and you can try and code these as common sense reasoning type things, or you can just make a calculus for each of them and just blast through them using, God knows what, satisfiability solvers and who knows what, and just get to the answer. And it becomes very sort of superhuman at that point. But it, same way that Wolfram Alpha can do that stuff. It just uses math and things like that to solve problems. And I think the main thing, I did catalog all this stuff. I mean, basically, there are sort of interrogative statements, questions about the world. There are assertions about the world, and there are commands, imperative statements. And one of the main areas that we have not encoded, which actually bizarrely is related to what we're talking about now, we have not encoded mental states in any of the stuff for Wolfram Alpha. So we don't encode anything like, I think that the sky is falling or something, if you understand what I'm saying. There's no I, there's no human consciousness in the representation of the world in Wolfram Alpha.
Yeah.
And that's kind of the notion, is that's one of the big pieces that's missing. Both that and actuation in the world. So anyway, I think that the goal is, the immediate use case is computational contracts.
Yeah,
And as well as, what's that?
So
I said that would be nice. Computational contracts.
Right. As well as a lot, I mean, for example, there are other use cases, recipes, instruction manuals, then regulations, et cetera, et cetera, et cetera. There's a lot that we haven't been able to encode. We can encode sort of entity property value type facts rather easily. We can encode other kinds of algorithmic facts rather easily. But this is, I mean, you can view this as a sort of meta modeling of the world type thing, granular meta modeling of the world.
Also goals, where you have to encode.
Yeah. Well, but goals, it depends what you mean by a goal. I mean, it depends how fluffy you want the goal to be. Ethical goals, not a chance.
Yeah, that's why it's hard.
So the historian in me just wants to know, so when you were testifying before the Senate, you were discussing something similar to this, but then the physics project came along. So were you thinking about this around that time?
I've been thinking about this for years, and I was finally getting ready to do it.
But were you getting ready to do it around that time?
Yeah.
Or afterwards?
Yeah. I was getting ready to do it then, and then the physics project arrived, and then I got derailed by the universe. And
I wonder if I'll ever tell you that excuse. Or at least the Rulli ad I was.
Yeah, right. No, I think, but I mean,
Wrong turn into Rulli ad. Yeah.
The problem is, yeah, exactly. The problem is this, that project, the Symbolic Discourse Language project, is in a sense a guaranteed success project. In the following sense, I mean, I completely know that it is a buildable thing. The physics project was not. The physics project might have just had nothing to do with physics. I mean, let's say the physics project had been, based on cellular automata, it just wouldn't have worked.
Mm-hmm.
I mean, it is, to me, still amazing how easily the whole thing has worked comparatively. I mean, there's many, a century of details, okay? But it's, paradigmatically, it's clear that it works. And it's, anyway, I mean, look, the thing that I don't know, I mean, each one of these things, this is a sort of challenge of project, each project, like the chemistry project, like immunology, like linguistics, like whatever, each one of those things has a certain, cost performance curve. You put a certain amount of effort in, you'll get a certain distance. Okay, which one is going to be the most important project is unclear. I mean, let's say the chemistry one worked, right? That would be incredibly important. It's like we'd have, molecular computing, and we'd understand how molecular biology works. And that would be, hugely important. On the other hand, that one has certain irreducible hair associated with it to do with the actual chemistry of molecules and who knows what else.
Yeah,
right?
Yeah.
And that one, I don't know how confident I should feel about that one, given how pathetic my knowledge of kind of high school chemistry is. I mean, It is amusing, because I can perfectly well follow the concepts of this reaction happens and how blah, 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 and all the graph theory stuff. But then when somebody says, and that's a, cyanogen, whatever it is, I haven't a clue what that is. I have no idea. I know nothing about the kind of the folk story of chemistry.
Well, we can talk about this at some other time, but what that means is that project's just going to involve, we'll have to have people who can do certain tasks and find a way of translating the important details so that you can do the analysis that you can do that others can't do, and we'll just have to have a way to divide the labor on that.
No,
Now,
I know, but look, I'm not actually that worried about it, because I actually think that knowing that it's called cyanogen is irrelevant, right? I can get a computer to tell me that.
well, that's what I'm saying.
I don't care.
But it's important for someone else. Someone else will, who's working on some aspect of it, might need to know that in order to arrive at some conclusion that's important.
I think it will be very similar to the physics project in this regard. Okay, so I think it's one of these cases where, when you do these projects in sort of innovative projects in various areas, you have to know just enough, but not too much about that area. If you know too much, you submerge, never to reemerge. I mean, if in the physics project, I have been lucky because I did know a lot about it. I know a lot about it as of 40 years ago, right? Which turns out to be kind of enough for many of the things we're doing. But I didn't know all of the details of every twist and turn of string theory. And that's probably just as well, because the level of what we're trying to do doesn't depend on that. And I think in the chemistry case, okay, the one big thing that I'm missing, which I need to add, is intuition about what actually happens when you do things with chemicals. Because the last time I tried to do that was 50 years ago, pouring random liquids together and seeing them froth and bubble and all this kind of stuff, right? And not understanding what the hell was going on. And only knowing, really not understanding anything, nothing.
And then deciding, okay, I'm going to go into physics.
Well, not quite. I mean, by the way, you do realize Rutherford's statement, science is physics plus stamp collecting. You realize that is an early statement of computational irreducibility. That's basically saying, in physics, we have managed to find computationally reducible laws. In chemistry, we have not. And in a sense, that has to do with this question of what the chemical observer really is. In other words, there are facts about chemistry where your nose is rubbed in computational irreducibility.
Now, I just want to point out that we were actually right in the middle discussing modus ponens before we started discussing philosophy, which led us to discuss.
I know, but I think that
just for perhaps Nick's sake, given the time zone, maybe we should let's determine the research plan for this week, or Nick,
right. The next step is to write the code.
Discussing this pattern app, this pattern applier, and Nick was asking whether or not it would be adequate to simply use modus ponens, and we were just discussing that. So that seems like an important.
Well, I think the answer is it's not quite right because it has extra hair. Okay, by the time you have to say, oh, and let's add an and let's add an equal sign and so on, that's got extra hair. I don't think it's necessary. I think we should just stick to this pure pattern applier, which just takes either subsets or trees, and
it's
just
it's just the matter of it's kind of pure, just a matter of initial condition. I kind of restricted, I kind of feed it already good expressions of trees that I know are useful, instead of trying to derive them from some kind of more simple initial condition. and all general.
Well, fair enough. Look,
possible rules.
so long as we can have something which does what I want, which is that you can take a rule like this and you can just say, have that be the initial TWP, have that be the initial pattern pool. Now have it apply it to itself and keep going. And all you've got is that rule being applied.
Okay.
So I'm saying, so long as we can do that, I don't think it's enough to have just one rule, right? You have to have two. Well, I'm not sure. I'm not sure. It may be important that it goes both ways. So, in the end, there's going to be another squiggly in mathematics, which is going to be something related to the univalence axiom. There's going to be another piece of the way that we form our human reference frame for mathematics. And it's probably going to be related to something like this: if it's equivalent, it's equal type thing. I mean, this characterization of what is the human reference frame for mathematics. Okay, the issue is, in physics, we think it requires only two axioms, namely computational boundedness times sequentiality. Okay, in mathematics, what are the analogous axioms? And, you see what I'm saying? And here's what I think might happen. I think, given those axioms, we may determine whether the continuum hypothesis is true or false.
That's very wishful.
Doesn't time sequentiality also hold?
Probably.
Okay.
Probably both. Probably computational boundedness and time sequentiality.
Well,
both.
computational boundedness, yes, also applies. So is the question whether or not we need to include additional ones?
Probably.
Wow.
I mean, maybe those are enough. But if it's those, then we will get general relativity. Because our structure, our underlying structure is similar enough.
Wait, do you mean the analog of that?
Yes, we will get the analog of general relativity in mathematics.
And do you think that's related to the continuum hypothesis?
No, I don't.
Okay, so what's the motivation for this claim about the continuum hypothesis?
Because
okay,
because here's why. Here's why.
Yeah.
If you say, I've got this molecular dynamics, okay, because the emergent structure is determined by our way of viewing things. Okay, if we were different, if we were aliens with, whatever, black holes for brains or something, we would perceive the mathematical universe differently. Okay, and for us, the emergent laws would be different. But given the way we are, there are probably definite emergent laws, and it might very well be the case. And the molecular dynamics doesn't really matter. In other words, we get emergent laws that depend on our observer characteristics more so than it depends on the molecular dynamics. And that's my claim, is that perhaps it will be the case that something like the continuum hypothesis is part of the emergent structure of mathematics. And
the hypothesis itself?
Well, whatever is true about the hypothesis would be, in other words, that given the emergent, okay, look, the continuum hypothesis might be like the presence of naked singularities in general relativity. Okay, what would that mean? That would mean there can be naked singularities, but not with the reference frames that we construct. Likely with kind of computationally bounded reference frames, you can't have naked singularities. And this might be the same way. That in principle, you could construct a way of viewing mathematics, a way of looking at the large scale aggregate so that the continuum hypothesis would be false or something. But in practice, given our characteristics as observers, you can't get to that. You see what I'm saying?
Yes, well, we've discussed it. We've discussed this before. So this is
well,
somewhat
another
of a recapitulation, but this is a good reminder. Yes.
Right, but that's the. I mean, that's the sense in which some of those things which could be undecidable, okay, here's the point. They could be undecidable at the molecular dynamics level. But when you go to the bulk limits, this is an interesting point.
Yeah, maybe write it down. Yeah.
Decidability by bulk in the bulk limit. There might be things which cannot be decided at the molecular dynamics level, but which inevitably come out a certain way for human-like mathematical observers. Or at a bulk scale, which is where humans, at the bulk scale, where mathematicians operate.
Now, I mean, I understand what you mean, but what does come out mean? You say inevitably come out.
Well, I mean that.
You don't mean that it
like
becomes, you don't mean
it
becomes decidable.
I mean, no, but look, decidability, the continuum hypothesis is not a decidability story. It's an independence story. Okay, well, I should say which are independent, which are undetermined, which depend on details at the molecular level, but which inevitably come out a certain way. That's what I really mean. In other words, you could set up axioms for set theory in which the continuum hypothesis is either true or false.
Okay.
That's why calculus is the same as doing bulk physics, but for mathematics. Like discrete and continuous calculus is the same as basically what we use for describing macro and micro physics is basically the same in the mathematical space. Just because we use the same tools.
That's an interesting claim. Okay, so your claim is calculus and continuum structures are used both in mathematics, both in physics and in mathematics. And so your basic point is that the description of the mathematical world, the continuous description of the mathematical world, but mathematics is a bit more than just continuous description, but it's a mathematical world is like the continuous description of the physical world. Okay, but show me general relativity. That's the question. Show me where
So there's a difference, like whether you derive general relativity using discrete evolution, or to have like a continuum limit of the discrete evolution itself.
Say that again. Sorry, what?
So there's a difference whether you have a continuous description into discrete like evolution, when you like, if you just evolve, because all mathematics are discrete in this sense, it's just a bunch of expressions, right?
Yes.
It's different than having the continuum limit itself of the same evolution.
Well, but you see, but I think
but
that, yeah.
But is it actually the same? Is it like continuum limit?
I think that mathematicians think in terms of the continuum limit, in a sense. You know, in some sense, mathematicians think in terms of the continuum. Automated theorem provers, you know, think in terms of the discrete symbolic expressions. I mean, this is the fluid dynamics analogy. You know, mathematicians are thinking in terms of these kind of continuous in meta-mathematical space.
But the system is continuous, not the mathematics itself.
Which system?
That mathematics describes the fluid.
Yeah.
But mathematics, any piece of mathematics, always discrete.
Human mathematics is always discrete, yes, because we think. I mean, but look, the point is that just like physics, we now believe is ultimately discrete, but our view of physics somehow approximates the continuum. I'm not sure. I'm not sure how this. I mean, the basic next step, as far as I'm concerned, is let's understand how this TWP generated mathematics works. Okay, and let's see how we can, for example, go from, you know, axioms of Boolean algebra. This approach will allow those axioms to puff out and generate all these other true facts about Boolean algebra. This is a generator of, this will be just like for that Euclid post, I used the axioms as rules. This is just going to be a purely substitutional way to puff out the rules to get new rules. Am I making sense?
But we're beginning with arbitrary rules.
No. Let's have a piece of code that can take any rule we want. Okay.
Well, yes, but the point is that we're supposed to begin with this pool of patterns.
I know. But I'm saying let's simplify our lives a bit, and start off, once we have the trees case, and start off looking at what happens if we start with known successful axioms. You see what I'm saying?
What will we be looking for if we basically start with our mathematics and our reference frame? What are we looking to get from there?
I don't know. We're looking to see whether we can see continuum, some kind of continuum limit. Okay.
Well, see, this is different than what we were discussing before, right? I was asking before, how difficult would it be to begin with arbitrary axioms and then try and identify a reference frame?
So there's three things we can do. Okay. One is start with known understandable axioms. Okay, maybe the one for semigroups, which is simpler. Okay.
Okay.
The second thing we can do is to do ruleology and start with just like I did in the NKS book, start with the simplest possible, you know, rules, the simplest possible TWPs. Okay, and just see what they do. Right.
Right.
And then ask the question, do these TWPs have universal properties? Is there universality in what they do? And is it the case that once you run it for a while, you wouldn't know where it came from?
Yes, right. So that's the question for the second approach. But what's the question for the first approach?
I don't know.
Where we begin with this, well,
I don't know. You just got to run it and see what happens. I don't know. The reason that first approach is interesting is that it's immediately interpretable. Okay, let me give you an example. For example, what I did in the Euclid post was I indicated where, look, here's the thing I did. I looked where in the, okay, so here we go. Okay, so this was looking at all possible statements of logic and then asking which ones are true.
yes.
But I think I didn't quite have it here. But what I wanted to do was to look at, well, you see, this is an interesting thing to do. This is an interesting thing because that is looking at, I mean, that isn't the morphisms, so to speak. That's the objects. That's generating objects and asking which of them connect to true. So it's a little different, but I mean, there's different ways to
but we haven't really defined truth.
No, I know. We've agreed that truth is just an arbitrary symbolic thing.
It seems weak.
What?
It seems like we should have some better way of understanding.
No, we do. We have what is generatable. Okay, so look.
But we can generate garbage in the pattern pool.
No, I understand we can generate garbage, but okay, in a particular slice of the Roolead, we will generate the stuff that we get in that slice, which we may consider not to be garbage. If you go off in a different slice, you've got garbage.
Mm-hmm.
I mean, I'm telling you, there is this nasty technical issue about rules versus expressions that keeps on hanging us up here. And that's why I really want to look at what happens, because see, for example, once we have a known axiom system and we are showing rule to rule to rule to rule to rule, like we're showing rule evolution, I want to see whether there's sort of some transitive closure of that just turns it into expression evolution.
Okay.
See what I'm saying? So that it doesn't matter that it was rule to rule to rule. It will be very redundant. This rule to rule to rule thing will be very redundant. What's the transitive reduction of what's going on there? Because that's a simplification that we can use in other places.
So but here's the other point of this, which is, I understand the argument that truth is determined by our reference frame, but it's not as simple. Not that you're saying this, but it's not as simple as we perceive something as true because our reference frame just determines truth. I mean, we can also consider falsity in our reference frame.
Absolutely, but I think what's much more the case is that truth is the generatability of a particular lemma. So it isn't the case that you can just say, oh, I can route my reference frame however I want. Any human specifiable reference frame has certain regularity associated with it. So once one thing is true, a whole boatload of other things have to be true too.
But the ones that aren't are false.
Yeah, for example. But I mean, but the whole point is that you don't get to knit You don't get to pick and choose your truth. You're
So
stuck.
is truth just a kind of artifact of our reference frame then in that way? And like, and it's very important to us, but it's very important to us basically because we're kind of indirectly describing
I
our
actually,
reference frame.
you know, okay. The philosophical logic people used to be very concerned about the difference between a statement and the statement, this statement is true.
Well, there's the deflationary theory of truth, right? This
How's
goes,
that?
well, this goes back to, what's his name? Deflationary theory of truth basically says that saying this statement is true is no different from the statement itself, if the statement happens to be true.
No, I don't know. I think that came from early linguistic philosophy.
But this is, oh yeah, Ramsey. This is going back to people.
Frank Ramsey, really?
Frank Ramsey was interested in truth in his philosophical writings.
Yeah, I don't know the whole. I would have more expected that was a Freddie Ayer thing, but I'm not sure. Anyway, it's all the same time and the same group of people. But the basic point of a statement versus this statement is true.
Mm-hmm.
You know, I suspect that the formal tagging of truth, I think the first of those is, can you generate the statement with this generative system? And the second is some kind of tagging mechanism. And you can no doubt set up the formalism to do either of these things. But I think the bigger picture is, I mean, I think it's probably more robust to think about it in terms of the generatability of the statement. That there's statements which can't be generated, you know, there may be statements which can't be generated within a certain reference frame or can't be seen there. I mean, unfortunately, reference frames, as we've learned from the token event graph formalism and things like that, there are many layers of reference framing. There's many issues about when are things equivalent, when do you aggregate tokens into states, when do you slice time. There are many different layers of equivalence. It will take a long time to untangle all those things.
What if falsity is just the boundary of the reference frame, where you can kind of collapse everything that could be true outside the reference frame, but you know it's not there, but you can still kind of discuss it. And so you basically just place it along the boundary.
It's possible.
I mean?
It's possible. I doubt that, but it's possible. I would think it's more like, look, you can discuss anything. I mean, you can write down the formal symbols. You just may not be able to get there. I mean, we can perfectly well say, go to the coordinates of, you know, a galaxy at redshift 5, right? Nothing stops us stating those coordinates. The fact that we can't get there is unfortunate. And so it is, I think, in metamathematical space. I don't think there's any trouble really in stating things. It's just like we've no idea. We're you know, I could state that the equation x to the 5 plus x to the 7 equals z to the 9 has solutions in, I don't know, in whatever, I don't know what it is, but I can state that, but it may be completely unreachable. I'm not sure. I think, look, the one mystery area I'd like to understand constructivism. I'd like to understand where that relates to all of this. And I'd like to understand model theory.
Well, you know, in constructive mathematics, like in Hammurabi type theory, you don't say anything's false. You basically just say you don't have a constructor for it. And there's one type that doesn't have a constructor, which is the empty type, and that's just a bold 0. And so anything that's false just maps to, or just maps to that type that doesn't have a constructor. And you could kind of treat the boundary as, wow, I wonder if you could treat the boundary as basically this reservoir of everything that you don't have a constructor for. And when you say it's false, you're basically just relegating it to this kind of unconstructible reservoir.
Well, but on the other hand, there are non-constructive proofs of things. Jonathan had been pushing last year this idea of understanding model theory and understanding non-constructive proofs as being on the border of proof cones.
Oh, well, that sounds somewhat similar. On the border of proof cones. Yes.
Yeah, I remember that. So it's like speed of light. Moving at the speed of light is like how non-constructivists move. The mathematical space.
Let's unpack that for a second. I mean, the concept of models is this concept, you know, to operate in a certain model is to do some kind of reference frame construction. See, I think there are multiple levels of reference frame, unfortunately, which is what makes it kind of complicated.
What are the different levels? Or what levels?
Well, because think about the token event graph. As I said, there's, you know, do you deduplicate events? Okay, that's one level of equivalence, right? Which tokens are collected into states? That's another level of equivalence. Which events lie in a particular foliation? That's another level of equivalence. See, so essentially, the theory of reference frames is a theory of how you build equivalence classes. And there are many equivalence classes to build.
Can you list those again? I'm going to write that down.
Yeah, right. I mean, so I'll make a list of it. Types of equivalence classes.
Wait, types of reference frames or types of, or
well, it's equivalence classes which build up to a reference frame in token event graphs. So I mean, the first one is equivalence between token token deduplication. Are these tokens the same? Okay. The next is states constructed from tokens. And the next is foliating events. And I think there are even more than that.
Let's see.
Just events deduplication.
What's that?
Just deduplication of events too.
Is that a separate thing?
Well, maybe it's just deduplicating those that have the same tokens as input and output.
Yeah, right. But anyway, so there are multiple different kinds of equivalence classing going on. Look, I mean, this question about models, model theory. I mean, the point of model theory, in some sense, is to answer questions without proofs. Is to be able to coordinatize, you know, in some sense, model theory coordinatizes mathematical space. I don't completely understand that statement, but something like that is true. So in other words, once you have a model, and again, that's something we could learn from looking at the perhaps really logical or perhaps, known axiom system example. You get what I'm saying?
Mm.
How does model theory coordinatize mathematical space? Is it the case that, it may be providing I don't know. I mean, that we need to understand that. That's something we need to understand from an actual exploration of actually generating proof chains. And once we understand model theory, in a sense, the statement of non-constructivism is a statement that there will be things that are provable, but not provable from models.
Well, what's a model, not in model theory, but in mathematical space?
I think it's a coordinate system. I think it's a
coordinate
foliation.
system.
I think what it is.
Is this related to the finite models that we wrote?
Yeah, I think yes, it's related to finite models. Yes, exactly.
Yes.
What would be like the
Makes it
meaning of
concrete.
the minimal like dimension of your finite model for your axiom system? Is it like dimension of space?
No, I don't see why it can't be quite small. I mean, I think the issue is, let's see, what a model tells one, like the finite models thing, tells one, for a given model, some theorems won't be true, right? For a given model, for a given model, not all general theorems, will be true, e.g. group theory, right? There may be theorems that are true. No, I'm sorry. More than the general theorems will be true. Okay, e.g. group theory. So in group theory, certain theorems are true of all groups. More are true for specific groups. Okay, so what that means in terms of TWPs is there will be additional TWPs, i.e., there are additional, I see how this works. There are additional TWPs that will be true if we just construct them with a particular model for the operator. You see what I'm saying? So let's imagine we have a TWP that says, f of a, b equals f of a, c or something. Let's say it's this, okay? So say we have that TWP. Okay. So we can determine that TWP, this TWP might be provable from the axioms we've chosen. Or it might just be that a specific model, e.g. finite model, for F and for the AB and for AB, etc., will make it true. You see what I'm saying?
Is this why the axioms are more brittle?
Not sure.
You remember that statement from before?
I remember the statement, yeah. I'm
Yeah.
not sure. But do you understand what I'm saying here? What I'm saying here is, let me show you. I mean, there will be axioms. Let's imagine that we have the axioms of semigroup theory, right? There will be statements. Okay, e.g., the axioms of semigroup theory, okay, which are just this. But there is a particular multiplication table which is symmetric and for which FAB equals FBA will be true, right? But that's not true in general. That cannot be deduced from the general statement for semigroup theory, from that general axiom,
Right.
semigroup theory, right? So that's saying there is a particular model in which more TWPs are deducible. So by picking a model, we're reaching more points in mathematical space somehow.
Yes. Okay.
Okay. Effectively,
Yes,
we're
yes,
probably
yes,
going
it
faster than the
makes
speed of light.
sense.
You know, by using models, we can go faster than the speed of proof. Because we can reach a TWP not reachable by proof steps. Because we can immediately reach. That would take many proof steps to reach. Does that make sense?
Yeah.
So what we should see is, yeah, given, right, we'll see this thing where we go and we apply proof steps and we generate buckets of TWPs, okay? Then we can also say, let's make a model. And given a model, we can just start generating oodles of TWPs that might have taken many steps to generate with proofs. That we can compare. Okay, so the comparison would be, yeah, okay, so e.g., look at TWPs that can be generated by many models. How close is that set to the set that can be generated by proofs? So for example, e.g., in pure arithmetic, in reverse mathematics, look at reverse mathematics and ask what theorems can robustly be generated for many models. Right, for many, I mean, and then, you know, there are many models, non-standard models of arithmetic. And some theorems, I mean, it's a weird case because those things are so far away in arithmetic, so to speak. Anyway, we got a plan, I think. This is actually very exciting. I mean,
Yes. Yes, I wasn't sure what was to become of this meeting, but it's been quite fruitful. Now, one hanging question, which is, before we began to discuss model theory, you suggested that there were three approaches to take. One was to begin with known axioms, such as semigroup axioms. The second was to begin with simple TWPs and see what they do, like do they exhibit universality? Was there some other third approach that you didn't mention on your mind?
hold on, let me think. Yes, to start off with all possible TWPs and fish things out of the soup. But I understand that one much less well. Look,
Okay.
I really also want to see with metamath, okay? I really want to see if we can see anything about where okay, in what we have described now, metamath, I think, is a collection of TWPs. Is that correct?
Not really.
What is it? What are the assertions in metamath?
This is like a sequence of statements, and it works like stack machine. So like you go for the sequence and put them on a stack, and then like each of the statement has some kind of arity. So it's like basically like a stack works.
Okay, we need to understand this. I don't understand that. We should talk about this another time. But we should understand that because the whole point is, okay, look, people will say when you talk about physics, how do you know if you've got the right physics? Okay.
Yeah.
And the answer is, well, because we already know things because they're in physics textbooks. Question is, we don't know the laws of mathematics. The best we can do is to look at some empirical data about mathematics. So insofar as we claim general laws of mathematics, our experimental data is formalized math systems. Well, so I mean, that's what we have to do. So look, okay, let me make a meta comment, okay? I feel like this is beginning to converge. I'm not to the point where I know exactly where, I mean, the primary things I don't know are really what this analog of general relativity actually is. What is the big statement that you can make about mathematics? You know, what Nick is implicitly claiming is that the big statement one can make is the continuum exists.
It's like it's like very, mathematics is kind of feels circular. So you can describe mathematics with mathematics, right? So it should be kind of, it feels like the continuum limit is exactly what we use to do continuous mathematics. No sense.
Oh boy. You see, but the continuum limit is in proof space, right? The continuum exists. So what we're doing in meta mathematics we're taking the continuum limit in proof space. How is that related to the continuum limit in quotes physical space, or in description space, so to speak? In other words, is the continuum, do you get what I'm saying?
Yeah.
I have a feeling that these things are all related through the famous Rouliad and through Grothendieck's hypothesis.
Hey.
Right, because that's what it would be, is that somehow this limit of proof space inevitably implies a geometry that the existence of the continuum. Okay, so this would be the bizarre claim. The bizarre claim is, if we've done enough mathematics, we will discover the continuum.
What does enough mean? What constitutes enough?
Well, whatever the continuum limit is. I mean, the continuum limit is an approximation. In other words, if we've done enough proofs, claim, if we've done enough proofs, we'll start seeing signs of the continuum. Or alternatively, if we do enough number theory, we'll inevitably discover analytic number theory.
It's like if you just add more and more theorems about integers,
Yeah.
the limit of those theorems can
Yes.
be just like some statement for real numbers.
Right.
In simple terms.
Very interesting.
Would it be the same, like instead of taking limit of theorems, if we also take the limit in a usual sense of numbers and just like apply them inside the theorems of our integers? Would it be
What
like,
do you mean?
it'd be the same limit? It's like if we apply this limit for numbers, so we just turn every number integer in our theorems to the real number. Would it be like?
But many theorems are not true anymore. I mean, unique factorization isn't true.
Yeah, because there's like, well, you have to take the limit carefully, not just replacing numbers, so maybe some qualifiers to quantify.
Yeah.
Like not for all integers, but for all reals. That's like, yeah, I don't know how it is.
But you see, but for example, you know, another thing we should see, even in the case of this, the TWPs. So one thing that's nice, I want to see proofs cones. And I'm a little bit concerned about seeing proof cones when there are TWPs.
What do you mean you're concerned?
Well, because I have a feeling that they will be the transitive closure of something, and that therefore you won't see locality of the kind that you need to see proof cones. I don't know. I mean, that's I don't know. That's what we have to look at. See, I mean, the existence of proof cones, the existence of light cones is a consequence of the fact that rewrites are somehow local in space. I'm pretty sure that proof cones will emerge. I claim probably proof cones will emerge if the entailment rules preserve information content in some sense. No, maintain bounded information content. That all that matters in the end is that you can't grab arbitrarily, complicated TWPs from somewhere else. See what I'm saying? Well, anyway, I mean, but that's the thing we got to see. That's why we've got to actually do this simulation. But I think these models may correspond to a certain reference frame, and different models may correspond to different, I don't think there'll be inertial frames. In a sense, relativity, special relativity, is some kind of statement about it's a statement about the equivalence of models. See what I'm saying? In other words, it doesn't matter what reference frame you use. Certain things will still be true.
Not the reference frame, even like model.
Which model you use, right? And that's the analog of special relativity. And the analog of the Einstein equations, well, the analog of the Einstein equations we have long believed to be something to do with the convergence of proof JD6.
Mm-hmm.
Again, we should be able to see that in this TWP thing. The problem is that I just want a realistic enough model of mathematics that we're not saying, oh, but that isn't really like mathematics, right?
Right.
And I think this TWP thing is a good enough model. Okay, here's what I want to be able to see. I want to be able to actually run our theorem prover and say, look, it's finding a path. It's finding the shortest path. It's finding the GD-sig. Right? We should be, given the TWP thing, we should be able to just put it into find equational proof to find a GD-sig. Do you agree?
Well, even if we're beginning from just the pool of patterns, we should be able to, can we use our theorem prover to find our reference frame when we begin just from
no.
No,
what we can do is we can find what series of TWP transformations we need to make to get to a particular place.
Within our reference frame.
No, it's just proof theoretic. There's no reference frame involved. Well, actually, wait a minute. That's not right. You see, again, I'm getting confused because there are different levels of reference frames here.
Right.
And I think the final level is probably this model theory level, but there are earlier levels as well.
Well, that makes it difficult to discuss.
It does, because there are multiple.
And because I've become accustomed to just using the term reference frame. And
I know. So we have to make that more granular, and I don't fully understand how. And yeah, look, anything that's been hanging around for 100 years isn't trivial to solve. So the fact that this is kind of complicated is not. I mean, you know, what we're doing, part of what we're doing here with these CWPs and things is we're recapitulating what people did, what Frege and people like that tried to do. And by the way,
in a very different way, but yes.
Well, it's not so different. I mean, they were just trying to make a model for mathematics. One of the important things here is that these TWPs may wind up being a very useful structure to have in our, in our language. That's just a thing we haven't really considered before.
Yeah, it might be important. I mean, much of this, I think, could find some purchase in computational contracts as well.
That's quite possible too.
I mean, this is a question that people ask quite often, which is how is it if you have different, you have computational contracts, you have different kinds of machines, blah, 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 they all have to coordinate, et cetera, et cetera. If you can actually understand something like relativity, it could probably translate into actually being able to, it will translate commercially into something like interoperability.
Yes.
Metamathematical special relativity will translate into something very kind of concrete and maybe.
Yeah, well, right. And I mean, basically, rule distance will translate into the difficulty of writing an interpreter.
That's what I mean. Yes, right. Well, that's what's fun about all this, is that it's not like we're doing research as a nonprofit.
Yeah, well, right. I mean, no, I mean, if things are deployable, then that's interesting. Yeah, right. No, I mean, there's a circle of ideas here that is beginning to coalesce. And I mean, I'm really struck by my little attempts to understand the history of philosophy. I'm really struck by how directly so much of this plays on all of that. I mean, shockingly extensively. And
I'm less shocked. I'm less shocked.
Well, I just didn't know about this stuff. I mean, I it's just like we can go through from Plato to Descartes to Kant to Heidegger. I mean, look, Heidegger had this book called Being and Time.
Yeah.
Right. What do you think it's about? I mean, I think it's about I think a bunch of these people have cottoned on to the idea that process is necessary to knit together the structure of the universe. In other words, that the disembodied atoms of space there's nothing there. That in order to have an existence, a reality, a being, you have to be progressing through time. In other words, computation knits together the structure of reality. And without it, you basically can't have consistent reality. For example,
have you read Process and Reality by Alfred North Whitehead?
nope,
Well,
might be related.
something called process philosophy in philosophy, and Whitehead is the kind of
I'm just, look,
as the originator of it.
I have this feeling, I'm beginning to have a feeling that just as our project is sort of a Rosetta Stone for mathematical physics, it might also be a Rosetta Stone for a bunch of these philosophy things.
Yeah.
I mean, in other words, the project concretifies just a boatload of these issues, which people have just been discussing in words. Anyway, I mean, any project that thinks it has a serious crack at explaining why the universe exists has to be has to have things to say about these things in philosophy. But anyway, I mean, look, the other project is I will try to write an essay that basically explains how all these things are related. And I'm just trying to ingest more and more philosophy, and then I'm going to start practicing by talking to people about it and get to the point where I feel somewhat confident. But I mean, it's clearly hopeless. I mean, like there's no way, there's no way that the full history of philosophy, just like, notice that I haven't gone into asking the question, how are we related to causal sets? How are we related to string theory and so on?
Right.
Because I think it's just too hard. I think this philosophy stuff is a little bit easier for me to do because it's softer. Like, in other words,
that's what you should tell the philosophers, by the way, when you speak with them.
What?
That you're speaking with them because you think that their field is softer and basically easier to handle than physics.
No. But I'll tell you why. To sketch a correspondence of our stuff with what Heidegger's done, for example. Okay.
Sure. Yeah.
It's a sketch. If you say, let me sketch how our stuff relates to string field theory, okay? I can give that sketch, but the people in the field expect more than that. And will probably need more than that to engage. Whereas I think the philosophers will need only a direction, and then they can engage. Not least because they actually listen to details. Whereas physicists don't.
Well, especially people in philosophy. The good people in philosophy of science really do.
Yeah, but I mean, but so, whereas in physics, they're going to say, unless you can show how the, such and such action is related to this, that, and the other with mathematics, you haven't got anything. Even if you can say intuitively, this is how it works. And
it's strange.
It's a different value system.
Yeah.
And it's one where, again, I also think, well, in both cases, there's a paradigmatic barrier. I don't know how difficult the philosophers will find. I have to say, my one data point of giving a philosophy talk about this stuff, I was impressed that the people cottoned on surprisingly quickly.
Where did you deliver the talk?
It was at this strange Center for the Future Mind, which is somehow, I think, in Florida, but the people were all over the place. But anyway, I was talking about the consciousness stuff, but people were asking very pertinent questions. I mean, I was impressed. Now, of course, it may be that I hadn't thought of this possibility. The reason they were asking pertinent questions is because Kant was very close to this, 300 years ago, and therefore they knew what questions to ask.
Still.
What do you mean?
Well, what do I mean? It's still nice that they were asked that that they weren't
that they could make the connection.
Yes, I mean, it's nice that they can make the connection. Yeah, that's my
right,
my whole point.
Right, but I mean, but the point is that it may be that the things I'm saying are not that different from things Kant said 300 years ago, 200 and something years ago.
Right.
And therefore, but it is non-trivial that the philosophers, but you see, the thing about philosophy is that unlike physics, well, these fields have different lifetimes of knowledge. Philosophy, people are still talking about Plato. Who talks about Heraclitus in physics except us? I mean, for us, yeah, anyway, you should go. I should go. I've got to work on some stuff.
Yes. What time is it in Moscow? 8:30 in the morning.
We're not even going to ask Nick.
Yes, it's 8:20. It's 8:26 a.m. Is that right, Nick?
All right, let's let Nick go.
Nick and I began meeting at around 12:30 his time, so he stayed up all night.
All right. Let's let everybody go.
We haven't even get to the MetaMath part.
Yeah,
we had 2 notebooks.
Oh, what was in the MetaMath notebook?
Just
well, if you open it, we're going to be here for at least
no, I'm not even gonna. I'm not going to do very much with it. I'm just going to open it. He says, famous last words.
Well, Nick can describe it in more detail, but we did encounter some pretty significant challenges in trying to represent more nuanced graphs. And what Nick was saying about it being a stack, you see this kind of these A, B, B, A, B, 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 A, B.
Okay, we're going to have to do this another time. I mean, and also, it's not obvious that MetaMath is the right formalized math system to use. I mean, maybe Lean is better. We have that data as well.
I think
this is just a small problem that I'm sure I'm gonna solve soon. We started just today, just to make actually a tree out of this sequence of statements that is like put on the stack.
I need to go.
Just
you guys
can
need to
make
go. To be continued.
To be continued. Cheers.
Right. See you later. Okay. Thanks, guys. Bye.
Bye.